Space has always fascinated us, but beyond the familiar planets and stars lie phenomena that challenge our understanding of the universe. Tonight we'll explore the cutting-edge ideas and discoveries shaping modern astronomy. From extreme planets to cosmic structures, we'll examine the evidence behind some of the most intriguing theories in space science. Join us as we uncover the extraordinary in our quest to understand the cosmos. WASP-12b has earned the ominous nickname the Planet of Death due to its extreme conditions and the bizarre fate it faces. This exoplanet orbits its host star at an incredibly close distance, completing a single orbit in just over 25 hours. Such proximity exposes the planet to intense gravitational forces and extreme temperatures, reaching over 2,000 degrees Celsius. These brutal circumstances create an environment unlike any found in our solar system. The primary reason behind this planetary destruction lies in the gravitational interactions between WASP-12b and its parent star. As the planet spirals closer, the star's gravity tugs at its atmosphere with such force that it begins to rip away the gaseous layers of WASP-12b. This gravitational stripping causes the planet to lose material continuously, effectively swallowing it piece by piece. In many ways, it is a cosmic game of tug-of-war that the planet cannot win. This runaway process is exacerbated by the intense heat from the star, which further expands the planet's atmosphere, making it even more susceptible to being pulled away. Studies show that WASP-12b is losing its mass at an astonishing rate, with experts estimating that it would be entirely consumed in a matter of tens of millions of years if its current trajectory continues. That staggering timeline may seem extended in human terms, but in cosmic terms, it is alarmingly swift. Observations of WASP-12b teach us not only about the dynamics of extreme planetary systems, but also about the life cycles of stars and the potential for similar fates facing other exoplanets. This fascinating case exemplifies the harsh realities of the universe, where planets can find themselves in perilous positions, highlighting the complex interplay between gravity and atmospheric conditions in the vastness of space. The phenomenon of diamond rain on Neptune and Uranus arises from the unique environmental conditions found within these distant ice giants. Both planets boast extreme pressures and temperatures deep within their atmospheres, conditions that are unlike anything we encounter on Earth. As researchers utilize advanced models and laboratory experiments, they have come to understand that the changes in pressure and temperature can lead to the conversion of carbon into diamond. In these frigid, high-pressure environments, methane, a molecule composed of carbon and hydrogen, breaks down under intense conditions. As the temperature rises and the pressure increases, the carbon atoms are freed from their bond with hydrogen. The liberated carbon atoms then form clusters that begin to crystallize as diamonds. These diamonds can grow over time, falling towards the core of the planet much like rain would fall on Earth. As they plummet deeper into the planet, these precious gems eventually fade from view. The immense pressures act to crush them further, leading potentially to the formation of larger diamond structures. Preliminary research suggests that the potential for massive diamond chunks may accrue in the heart of these planets, creating extraordinary and extreme geological phenomena. This striking concept reshapes how we comprehend the internal dynamics of our solar system's gas giants. The idea of tracing diamond rain offers both a scientific explanation for unusual atmospheric phenomena and a tantalizing glimpse into the rich complexities of planetary formation and evolution within the cosmos. While the diamonds themselves may never reach the surface, the journey and transformation they undergo reveal just how extraordinary the conditions on these distant worlds can be. On exoplanet HD 1897733b, the phenomenon of glass rain is caused by a unique combination of extreme heat, high winds, and atmospheric conditions that defy our traditional understanding of weather. Located about 63 light-years away from Earth, this gas giant orbits its star closely, leading to scorching temperatures that can soar to around 1,800 degrees Celsius. Such intense heat fundamentally alters the materials present in its atmosphere. The primary components of HD 1897,733b's atmosphere include various molecules, including silicates. Under the extreme temperatures and pressures found on the planet, these silicates can vaporize and then condense as the atmospheric conditions change. Winds on this exoplanet reach astonishing speeds, exceeding 2 kilometers per second. These violent gusts carry the vaporized silicates up to higher altitudes, where they cool and precipitate back down towards the surface in the form of glass shards. This constant cycle of vaporization and condensation results in a relentless rain of glass, creating a truly hostile environment. The glass drops fall sideways due to the ferocious winds, leading to a scene that is both awe-inspiring and terrifying, as the glass would be sharp and dangerous. The relentless nature of this weather cycle raises fascinating questions about the diversity of planetary atmospheres and the extremes that can exist beyond our own solar system. The existence of glass rain on HD 1897,733b particularly emphasizes the breadth of environmental conditions that exoplanets can exhibit. Observing and understanding such phenomena help astronomers gain deeper insights into the atmospheres of distant worlds, showcasing the incredible variety of weather patterns that exist throughout the universe. Kelt 9b holds the title of the hottest known exoplanet, and it does so with staggering temperatures that can exceed 3,000 degrees Celsius. This extraordinary heat stems from its incredibly close orbit to its host star Kelt 9, which is an incredibly hot and massive A-type star. Kelt 9 is about 2.5 times more massive than our Sun and has surface temperatures that can reach up to 30,000 degrees Celsius, making it much hotter than the Sun. The close proximity of Kelt 9b to its star dramatically influences its atmospheric conditions. Orbiting its star in just under 1.5 days, this exoplanet experiences relentless exposure to extreme levels of radiation and heat. The intense energy from Kelt 9 effectively strips away the atmosphere of Kelt 9b, creating an environment where the temperature rises to a level that is unfathomable by terrestrial standards. The atmosphere may be composed of gases such as iron, which can exist in a gaseous state due to the extreme conditions. In comparison to our Sun, Kelt 9 is a beacon of heat and radiation. The Sun has a surface temperature hovering around 6,000 degrees Celsius, far cooler than the surface of Kelt 9. This comparison highlights the extreme nature of Kelt 9b's environment, emphasizing how even a relatively small change in distance from a star, combined with the star's intrinsic properties, can lead to wildly different planetary conditions and an entirely new understanding of what is possible in our universe. Kelt 9b not only serves as a benchmark for extreme exoplanetary conditions, but also challenges scientists to rethink existing notions about planetary atmospheres and habitability. The thermal extremes on Kelt 9b provide a fascinating case study, shedding light on the diversity of planetary environments that exist beyond our solar system and offering insights that deepen our understanding of stellar and planetary evolution. Corot 7b has earned the nickname Lava Planet due to its intensely hot surface temperatures, which can reach around 1,000 degrees Celsius, creating conditions conducive to molten rock. This exoplanet orbits its star at an extremely close distance, completing a revolution in approximately 20 hours. Such proximity subjects Corot 7b to relentless radiation, contributing to its hellish landscape where volcanic activity is likely common. The extreme heating causes the planet's surface to be partially molten, leading to lakes of lava that can dominate large swathes of the terrain. Unlike Earth, where plate tectonics and various geological processes contribute to a diverse landscape, Corot 7b's surface is markedly smoother and transformed by continuous volcanic activity. The combination of high temperatures, immense pressure, and a lack of atmosphere creates a very different planet, one characterized more by its extreme heat than by the diverse conditions found on Earth. In contrast to Earth, which has a stable atmosphere that supports life and regulates temperature, Corot 7b appears to have a tenuous atmosphere, if it exists at all. The intense heat likely prevents a significant atmosphere from forming, leading to a lack of weather systems or natural cycles similar to those we experience on our planet. This makes Corot 7b a fascinating, albeit inhospitable, environment for study, guiding scientists toward understanding how different planetary systems can evolve under various stellar influences. The lava planet serves as a striking example of the diversity found within exoplanetary climates and compositions. As researchers continue to discover and investigate such extreme worlds, they gain valuable insights into the processes governing planetary formation and dynamics, which in turn enhance our understanding of Earth's own geological history and its place within the cosmos. Rogue planets, those mysterious celestial bodies that drift through the galaxy without a host star, possess a remarkable ability to survive despite the cold darkness of space. These planets may have formed in the same manner as typical planets, orbiting stars during their early life. However, violent gravitational interactions, such as those encountered during close encounters with other celestial bodies, can eject them from their original systems, sending them hurtling into the interstellar void. One key factor in the survival of rogue planets lies in their internal heat. Many of these planets retain heat generated during their formation, as well as heat from radioactive decay of elements within them. This residual warmth can allow rogue planets to maintain a semblance of geological activity and potentially sustain some form of atmosphere, albeit a thin one. In the absence of a star, they may also experience prolonged cooling, but this initial heat can keep their interiors active for extended periods. Rogue planets may also be home to unique forms of atmospheric chemistry. Some research suggests that these planets could have thick atmospheres, potentially consisting of gases like hydrogen or ammonia, which could trap heat. This could create temporary environments where liquid water might exist, particularly if the planet has enough mass to hold onto its atmosphere against the vacuum of space. Although rogue planets face challenges in maintaining habitable conditions, their unique characteristics offer scientists a fascinating insight into planetary formation and survival. The existence of such planets challenges our conventional understanding of planetary systems, expanding the boundaries of what we consider when searching for potentially habitable environments in the universe. The intriguing nature of rogue planets invites continued exploration, encouraging scientists to uncover the secrets of these wandering worlds and their role in the cosmos. Joan 1407b, often referred to as Super Saturn, stands out in the universe due to its astonishing and elaborate ring system. Discovered in 2012, this exoplanet resides approximately 400 light-years away in the constellation Centaurus and showcases features that rival and, in some cases, exceed those of Saturn. One of the most striking aspects is the sheer size of its rings, which are estimated to span over 100 times the radius of the planet itself. These rings are not only vast, but also incredibly massive, indicating a complex structure that could vary in density. The ring system of Joan 1407b consists of multiple bands, potentially made up of ice and rock particles, similar to those found in other ring systems, including Saturn's. However, what sets Joan 1407b apart is the possibility of these rings being surrounded by orbiting moons or moonlets, which may contribute to the intricate dynamics of the system. Recent observations suggest that the rings are likely composed of various materials, and they could also harbor gaps and waves created by the gravitational influence of these moons. Another intriguing feature of Joan 1407b is its potential size. The planet itself is thought to be significantly more massive than Saturn, with estimates placing it at around 20 times the mass of Jupiter. This immense mass might be a contributing factor to its complex ring structure, as stronger gravitational forces can lead to more intricate scenarios involving the formation of moons and the shaping of ring characteristics. The combination of its extraordinary mass and stunning ring system elevates Joan 1407b as a focal point of study for scientists. This super Saturn expands our understanding of planetary systems, illustrating the variety of structures and characteristics that can arise beyond our own solar system. By investigating such unique features, researchers can glean insights into the processes governing planetary formation and ring dynamics, enriching our knowledge of the universe's cosmic tapestry. Gliese 436b has earned the captivating nickname Icefire Planet, and this unusual designation stems from its extreme and seemingly contradictory environmental conditions. Orbiting its host star at a remarkably close distance, this exoplanet experiences temperatures that can exceed 800 degrees Celsius on its surface. However, despite this intense heat, a significant portion of the planet is believed to be composed of water in its solid form, creating a unique juxtaposition of ice and fire. The physical structure of Gliese 436b showcases how it maintains stability despite these extreme temperatures. The high pressures experienced in its gravitational field play a crucial role. When water is subjected to the incredible pressures found on Gliese 436b, it can undergo transformations that allow it to exist as a solid even at high temperatures, from a state that might otherwise be gaseous under different conditions. This situation results in a unique form of ice that withstands these heat levels, creating a landscape that could feature ice formations and potentially even oceans beneath a thicker gaseous envelope. Adding to the complexity of this planet's nature is its atmospheric composition. The atmosphere consists primarily of hydrogen and helium, which allows for the retention of heat. This creates conditions where water can exist in different states, maintaining the solid form while the external environment remains scorching. The interplay of pressure and temperature leads to a unique state of matter, highlighting how various planetary environments can converge and transform traditional understandings of ice and fire. The fascinating characteristics of Gliese 436b not only challenge our perceptions of planetary formation, but also underline the diversity of exoplanets across the universe. Investigating the mechanisms that allow this ice-fire planet to exist broadens our comprehension of the extreme conditions that can be found among the myriad worlds beyond our solar system. Understanding these dynamics enriches our scientific discourse and offers captivating insights into the processes that govern planetary characteristics and atmospheric chemistry. TRES 2b holds the title of the darkest known exoplanet, primarily due to its exceptional ability to absorb nearly all the light that falls upon it, reflecting less than 1% of that light. Located approximately 300 light-years from Earth, this gas giant orbits very close to its host star, leading to extreme temperatures that can reach over 1,000 degrees Celsius. The combination of its proximity to the star and its unique atmospheric properties contributes to its striking darkness. The composition of TRES 2b's atmosphere plays a significant role in its extraordinary light-absorbing capabilities. Scientists believe that the planet's atmosphere consists of materials such as sodium and potassium, which can create a haze that darkens its appearance. These compounds might work in tandem with other elements to form clouds that not only absorb visible light, but also block much of the reflected light. This results in a surface that is more akin to the blackness of charcoal than to the reflective surfaces we see on Earth or even on other gas giants. Another fascinating aspect of TRES 2b is its role in understanding the physics of exoplanet atmospheres. The planet's remarkable darkness serves as a natural laboratory for researchers, providing insights into how light interacts with different materials and compounds under extreme conditions. This can enhance our understanding of similar exoplanets, especially those with comparable atmospheric compositions and temperatures. The discovery of TRES 2b's extreme darkness complicates our assumptions about planetary characteristics and their visibility. It challenges scientists to rethink how we identify and categorize exoplanets based on light reflection and absorption. By studying such extraordinary worlds, researchers not only broaden their understanding of the diversity of planetary atmospheres, but also gain valuable knowledge about the conditions that can exist beyond our solar system. The atmosphere of HD 209458b commonly referred to as Osiris, undergoes a fascinating and dynamic process of evaporation that is largely driven by intense stellar radiation. This exoplanet orbits very close to its host star, completing an orbit in less than 4 days. Such proximity subjects Osiris to extreme temperatures, which can soar above 1,000 degrees Celsius. The heat wreaks havoc on its atmosphere, causing it to lose significant amounts of gas into space. The high-energy radiation emitted by the host star plays a crucial role in this atmospheric evaporation. As the radiation bombards the planet, it provides enough energy to strip away particles from the upper layers of the atmosphere. This process, known as thermal evaporation, occurs when the kinetic energy of the atmospheric particles increases to the point that they can escape the planet's gravitational pull. Consequently, lighter elements, particularly hydrogen and helium, become more susceptible to being lost, forming a tail-like structure that stretches out into space. Observational studies have revealed that Osiris is losing a considerable amount of its atmospheric mass, estimated at thousands of tons per second. This loss is not static. The extent and rate of evaporation can fluctuate depending on the intensity of the stellar radiation and the planet's atmospheric composition. As heavier molecules like water vapor and carbon monoxide may also evaporate at lower rates, their presence contributes to the intricate dynamics within the planet's atmosphere. The evaporation of HD 209,458b's atmosphere provides vital insights into the atmospheric processes that affect exoplanets, particularly those that orbit close to their stars. By studying this extraordinary case, scientists improve their understanding of how planetary atmospheres can evolve and how various factors contribute to the habitability of worlds under different stellar conditions. The fascinating processes observed in Osiris serve as a reminder of the diverse behaviors exhibited by exoplanets throughout the cosmos. Galactic filaments are vast, thread-like structures in the universe made up of galaxies, dark matter, and gas. These formations are critical to the structure of the universe, serving as the most extensive components of what scientists refer to as the cosmic web. The cosmic web is the large-scale structure of the universe, characterized by a network of interconnected filaments, with galaxies found along these filaments and vast voids in between. These filaments form as gravitational forces cause matter to clump together over billions of years. As the universe expanded from the Big Bang, initial tiny density fluctuations grew due to gravity, leading to the accumulation of dark matter and gas. This gravitational attraction led to the long, thin structures we observe today, where galaxies and clusters of galaxies align along these filaments. Essentially, they act as highways, guiding the flow of matter and energy through the universe, all while shaping its large-scale architecture. Galactic filaments not only serve as connectors between galaxy clusters, but also as crucial sites for star formation. Within the dense regions of these filaments, gas can cool and condense, leading to the birth of new stars. This ongoing process highlights their role in the life cycle of galaxies and provides insight into the evolution and behavior of cosmic structures. Overall, the existence and properties of galactic filaments enhance our understanding of the universe's formation and evolution. They illustrate the intricate connection between various components of the cosmic web, revealing a harmonious blend of gravitational influences and matter distribution that shapes the large-scale organization of the cosmos. Through the study of these fascinating structures, astronomers continue to unlock the mysteries surrounding the formation of galaxies and the dynamics of the universe itself. Supermassive black holes play a pivotal role in the evolution of galaxies, significantly impacting their formation, structure, and overall dynamics. Typically found at the centers of large galaxies, these colossal entities can possess masses equivalent to millions or even billions of suns. Their immense gravitational pull affects the surrounding stars and gas, shaping the dynamics within the galaxy and influencing its evolution over cosmic timescales. One of the primary ways supermassive black holes influence galactic evolution is through their feedback mechanisms. As matter falls into a supermassive black hole, it forms an accretion disk that heats up and emits tremendous amounts of energy, particularly in the form of X-rays and jets of high-energy particles. This energetic output, known as active galactic nucleus activity, can regulate star formation in the galaxy. The energy dispersed can heat or expel surrounding gas, inhibiting the collapse of material that would otherwise create new stars. Consequently, the presence of a supermassive black hole can play a complex role in either promoting or suppressing stellar formation within its host galaxy. Additionally, supermassive black holes can also influence the overall morphology of galaxies. Their gravitational forces can help maintain the structure of the galaxy, affecting the motion and distribution of stars. For example, in spiral galaxies, the gravitational influence of the black hole can help create and maintain the balance of the galaxy's spiral shape. Over time, interactions with surrounding stars and gas can also lead to the black hole growing in mass, which further strengthens its influence on the evolution of the galaxy. Moreover, as galaxies evolve, the mergers between them often result in the merging of their respective supermassive black holes. Such events can lead to significant energy release and can impact the evolution of the newly formed galaxy, amplifying any active galactic nucleus activity. These interactions contribute to the complex chain of events that lead to the diverse structures we observe in the universe today. Through these various mechanisms, supermassive black holes not only influence their host galaxies, but also challenge our understanding of large-scale cosmic processes. Their study offers critical insights into how galaxies form and evolve over time, providing a deeper understanding of the interplay between gravity, dark matter, and the life cycle of stars in the grand tapestry of the universe. Galactic collisions are primarily caused by the gravitational forces between galaxies as they move through space. The universe is not static. Instead, it is in constant motion due to the expansion driven by dark energy and the interplay of gravitational attractions. When galaxies are relatively close to one another, their mutual gravitational pull can lead them to alter their trajectories, eventually resulting in a collision. These interactions can occur over billions of years as galaxies drift through the cosmic landscape, often influenced by the presence of nearby massive galaxies or galaxy clusters. When galaxies merge, the process is complex and dynamic, often unfolding over an extended time frame. Initially, as two galaxies approach each other, their gravitational influences create tidal forces that can distort their shapes, pulling out streams of stars and gas. These tidal interactions result in the formation of beautiful tidal tails, elongated structures of stars and gas that trail behind the two merging galaxies. As the galaxies continue to collide, their gas and dust can dramatically increase star formation rates, leading to what is known as a starburst event. During this period, new stars are born at an accelerated pace due to the compression of gas clouds. Eventually, as the galaxies pass through each other, they will settle into a new equilibrium. In many cases, the nuclei of the merging galaxies will also coalesce, leading to the formation of a new supermassive black hole at the center of the merged galaxy. This newly formed galaxy may exhibit a different structure, potentially evolving into an elliptical shape, which contrasts with the spiral forms of the original galaxies. The merger process not only affects the individual galaxies, but also has significant implications for their new environment, including the gravitational dynamics of nearby galaxies. Overall, the phenomenon of galactic collisions and mergers plays a fundamental role in the larger picture of cosmic evolution. By studying these events, astronomers gain valuable insights into how galaxies grow, evolve, and interact over time. The processes that occur during and after a galaxy merger can illuminate our understanding of galaxy formation and the complex interplay of dark matter, star formation, and supermassive black holes, ultimately enriching our grasp of the universe's structure and history. The formation of galactic bars in spiral galaxies is a captivating topic in astrophysics, and several theories have emerged to explain this striking structural feature. One prominent theory is the gravitational instabilities that occur in the disk of a galaxy. In many spiral galaxies, the distribution of stars, gas, and dark matter creates regions of varying density. When the density becomes sufficiently high, instabilities can arise, leading to the development of a bar that extends across the center of the galaxy. This elongated structure allows matter to redistribute itself, facilitating the flow of gas towards the nucleus. Another key mechanism attributed to bar formation involves the interaction between the different components of a galaxy, particularly between the stars in the disk and the gravitational influence of the central supermassive black hole. As stars orbit the center of the galaxy, their motions can become organized into a coherent structure, resulting in the formation of a bar. Over time, interactions among these stars can lead to a more pronounced and stable bar shape, which can then influence the orbital dynamics of other stars in the galaxy. Furthermore, bars can also form as a result of external forces. When galaxies undergo interactions or mergers, the gravitational forces from nearby galaxies can induce a bar-like structure in the disk of a spiral galaxy. These interactions can bring gas and stars into a more ordered state, enhancing the likelihood of bar formation. Such external influences highlight the dynamic nature of galaxies and the importance of environmental factors in shaping their evolution. Theories regarding the formation and persistence of galactic bars are still an active area of research. Computer simulations and observations are essential in developing a comprehensive picture of how these structures evolve over cosmic time. Bars can influence the star formation processes within galaxies, regulate the dynamics of gas flow, and even play a crucial role in the eventual fate of the galaxy itself. The study of galactic bars not only enhances our understanding of galaxy structure, but also provides insights into the broader processes that govern galactic evolution in the universe. Galactic magnetic fields play a critical role in shaping both star formation and the overall architecture of galaxies. These invisible forces exert pressure on the charged particles within the interstellar medium, which is a vast region filled with gas and dust. When star formation occurs, clouds of gas collapse under their own gravity to create new stars. However, magnetic fields can either facilitate or impede this process. When a massive cloud begins to collapse, the magnetic field lines can help to stabilize it by providing additional pressure that counters gravity. This phenomenon can lead to a slower and more organized formation of stars, allowing for the development of dense clusters rather than chaotic bursts. In contrast, if a magnetic field is weak or poorly oriented, it may not provide sufficient support, leading to rapid and potentially less efficient star formation. Thus, the strength and configuration of magnetic fields can significantly influence the rate and style of star formation within a galaxy. Moreover, magnetic fields help govern the dynamics of gas flows within a galaxy. These fields can shape the spirals of galaxies, acting as a guide for the movement of ionized gas. This movement can, in turn, affect how matter accumulates to form new stars and planets. The interplay between gas dynamics and magnetic fields can lead to intricate structures within galaxies, facilitating the creation of stellar nurseries where new stars are born. Recent observations have revealed fascinating insights about the magnetic fields in various galaxies, suggesting their influence may extend to the behavior of cosmic rays and the heating of gas. This means that galactic magnetic fields not only contribute to the current state of star formation, but could also affect long-term processes such as galaxy evolution and the distribution of stellar populations. Understanding these fields is essential for deciphering the complex tapestry that constitutes our universe. Galactic winds are powerful outflows of gas that are primarily driven by energetic processes occurring within a galaxy. These winds can be generated by various phenomena, including supernova explosions, intense star formation, and active galactic nuclei, which are supermassive black holes at the centers of galaxies. As massive stars reach the end of their life cycles and explode, they release enormous amounts of energy. This energy can blow away surrounding gas, creating high-velocity outflows that can escape a galaxy's gravitational pull. One of the profound impacts of galactic winds is their ability to enrich the intergalactic medium with elements produced in stars. When gas is expelled from a galaxy, it often contains a mix of primordial hydrogen and helium, along with heavier elements generated through nuclear fusion, such as carbon, oxygen, and iron. This not only affects the chemistry of the intergalactic medium, but also influences the evolution of future generations of stars and galaxies. Essentially, galactic winds contribute to a cycle of material that shapes the overall structure of the universe. The dynamics involved in these winds also play a role in regulating star formation rates within galaxies. If the outflow is sufficiently powerful, it may remove gas necessary for the creation of new stars, effectively quenching star formation. Conversely, this outflow can also create shockwaves that compress surrounding gas, potentially triggering new star formation in regions that would otherwise be too diffuse to collapse. In addition to these processes, galactic winds can create feedback mechanisms that interact with the larger cosmic web, the vast structure of interconnected galaxies and dark matter. As winds travel through the intergalactic medium, they compress and heat the surrounding gas, contributing to the thermal and magnetic structure of the universe. This interconnectivity highlights the significant role that galaxies and their winds play in the broader narrative of cosmic evolution. Galaxy clusters, the largest gravitationally bound structures in the universe, form through a complex process that spans billions of years. Initially, small density fluctuations in the early universe acted as seeds for gravitational attraction. Over time, these slight variations allowed matter to accumulate, leading to the formation of protoclusters. These are dense regions of gas and dark matter where galaxies begin to coalesce. As gravity pulls more matter into these protoclusters, they grow in size and complexity. Galaxies merge and interact within these clusters, further increasing their mass. The process is fueled by the infall of surrounding gas and dark matter from the cosmic web, which is a vast network of filaments that connect galaxies and clusters. The interactions between galaxies within clusters can create spectacular phenomena, including galaxy mergers and the formation of new stars triggered by gravitational forces. As clusters evolve, they undergo a process called hierarchical clustering. This means that smaller clusters and groups of galaxies merge to form larger structures. In this dynamic environment, clusters can grow in mass and change in shape. As they interact, they may also experience significant cooling of their intergalactic medium, leading to the emission of X-rays as hot gas is heated to extreme temperatures. This X-ray emission provides crucial insights into the properties and mass of the cluster. Over cosmic time, galaxy clusters can also influence their environments. Their immense gravitational fields can trap hot gas, preventing it from escaping and contributing to further galaxy formation. Additionally, the presence of a cluster can affect the motion and distribution of dark matter in its vicinity. Understanding how galaxy clusters form and evolve helps astronomers piece together the history of the universe, offering clues about the interplay between dark matter, normal matter, and cosmic expansion. Dark matter plays an essential role in shaping the structures of galaxies and the universe at large. Although it cannot be observed directly, its presence is inferred from its gravitational effects on visible matter, such as stars and gas. Initially theorized in the early 20th century due to discrepancies in galaxy rotation speeds, dark matter has become a cornerstone of our understanding of cosmic structure. The gravitational influence of dark matter extends far beyond the visible components of galaxies. It forms a vast halo around galaxies, providing the necessary gravitational pull to hold together the stars and gas that make up their visible structures. This dark matter halo not only helps explain why galaxies rotate at the speeds they do, but it also plays a critical role in the formation and evolution of galaxies themselves. As gas begins to cool and collapse under gravity to form stars, dark matter halos create the gravitational wells that attract this material, guiding it into denser clumps. The distribution of dark matter within a galaxy influences its overall shape and behavior. For instance, in spiral galaxies, dark matter is distributed in a roughly spherical halo, which extends significantly beyond the visible limits of the galaxy. This distribution can determine the galaxy's angular momentum and stability, affecting the formation of spiral arms and the dynamic interactions between different components. Similarly, in elliptical galaxies, dark matter can contribute to their smoother, more homogeneous structures. Beyond individual galaxies, dark matter also plays a vital role in clustering on larger scales. It contributes to the formation of galaxy groups and clusters through gravitational interactions, forming a web-like structure across the universe known as the cosmic web. Understanding dark matter is crucial for astronomers attempting to unlock the mysteries of cosmic evolution, as it holds the key to the gravitational forces that bind galaxies together and drive their development over billions of years. Quasars, or quasi-stellar objects, are extraordinarily bright and energetic phenomena observed at the centers of some galaxies. They are powered by supermassive black holes that have accreted vast amounts of gas and dust. The formation of a quasar typically begins with the collapse of material into a supermassive black hole, usually found at the core of a galaxy. As matter spirals inwards, it forms an accretion disk, heating up to extreme temperatures due to friction and gravitational forces, which subsequently causes it to emit immense amounts of energy across the electromagnetic spectrum. The relationship between quasars and galactic evolution is profound. Quasars often represent an active phase in the life of a galaxy, particularly during periods when it undergoes significant growth and transformation. In the early universe, many galaxies experienced intense bursts of star formation and activity. During these periods, the feeding of the supermassive black hole can result in a quasar shining as one of the brightest objects in the universe, outshining all the stars in the host galaxy combined. This luminosity can make quasars visible from great distances, allowing astronomers to study their properties and the conditions of the early universe. Additionally, the energy released by quasars can influence the evolution of their host galaxies. Powerful jets of material that emerge from the black hole can interact with the surrounding gas, heating it and preventing it from cooling to form new stars. This feedback mechanism can regulate the rate of star formation within the galaxy, shaping its future development. As a quasar exhausts its fuel, the black hole can eventually enter a quieter phase as the galaxy transitions to a more stable state. Observations suggest that many of the massive galaxies we see today experienced an active quasar phase during their history. Thus, studying quasars provides invaluable insights into not only the nature of black holes but also the processes that drive galaxy formation and evolution in the cosmos. Quasars serve as a window into understanding the interplay between these colossal black holes and their host galaxies, illuminating a crucial chapter in the story of the universe. The formation of elliptical galaxies is a fascinating topic within astronomical research, and several theories attempt to explain how these distinct structures come into being. One prominent theory is that elliptical galaxies primarily form through the merging of smaller galaxies. When two or more spiral or dwarf galaxies collide and merge, the gravitational interactions can lead to a redistribution of stars and gas, resulting in a more rounded, spheroidal shape characteristic of elliptical galaxies. This process often occurs in dense environments, such as galaxy clusters, where encounters are more frequent. Another essential concept in the formation of elliptical galaxies is the role of gravitational relaxation. As galaxies merge, their stars interact gravitationally, leading to a randomization of their orbits. Over time, this process smooths out the initial disk-like structures, converting the system into a more isotropic distribution of stars. This relaxation helps produce the elliptical form, as the stars within the galaxy no longer have a preferred direction of motion, but instead occupy a range of orbits throughout the space of the galaxy. The so-called monolithic collapse model is another theory that explains the formation of elliptical galaxies through a single, rapid process. In this scenario, a large cloud of gas and dust collapses under its own gravity, forming a very massive protostar. As the core collapses, stars form rapidly in a burst of activity, resulting in a compact system. This early phase can favor the formation of older red stars, lending early elliptical galaxies their characteristic color. In this model, the rapid star formation exhausts the available gas, leaving the galaxy with little to no new star formation after its initial development. Finally, studies have suggested that the present-day environment of elliptical galaxies also plays a role in their evolution. They can continue to grow by accumulating gas from their surroundings or by merging with smaller galaxies, which can further affect their brightness, size, and stellar populations. While these theories provide a framework for understanding the complex processes behind elliptical galaxy formation, the interplay of interactions, gas dynamics, and gravitational influence continues to be an active area of research in cosmology. The Great Attractor is a gravitational anomaly located in a region of space within the vicinity of the Virgo cluster. This large concentration of mass is drawing galaxies, including our own Milky Way, toward it at significant velocities. The exact nature of the Great Attractor remained somewhat elusive for many years due to its position in a part of the sky obscured by the Milky Way's plane, which contains gas and dust that hinder observations. The Great Attractor is thought to be primarily associated with a supercluster of galaxies known as the Laniakea supercluster, which includes the Perseus-Pisces supercluster and many other galactic structures. It contains an immense amount of unseen mass, much of which is believed to be dark matter. This dark matter interacts gravitationally with visible matter, creating a gravitational pull that affects the motion of galaxies over vast distances. It is estimated that the mass of the Great Attractor could be the equivalent of millions of times that of our Sun, contributing to its strong gravitational influence. The dynamics of our universe suggest that galaxies are not static but are instead moving through the cosmic web, influenced by the gravitational effects of massive structures like the Great Attractor. In fact, our local group, a collection of galaxies that includes the Milky Way and Andromeda, is currently moving toward this anomaly at a speed of nearly 700 kilometers per second. The journey toward the Great Attractor is part of a larger cosmic flow, indicating that these superluminous regions have been pivotal in the formation and distribution of galaxies across the universe. Understanding the Great Attractor is crucial for comprehending the large-scale structure of the universe, illuminating the dynamics of galaxy motion and interaction within the broader cosmic web. As astronomers continue to study this mysterious region, they aim to piece together the interconnected puzzle of forces that shape the universe and its vast networks of galaxies. The existence of supermassive black holes in the early universe raises intriguing questions about their formation and growth. Observations have revealed supermassive black holes existing just a few 100 million years after the Big Bang, leading researchers to explore various theories that could explain their rapid emergence. One leading hypothesis involves the concept of direct collapse black holes. According to this theory, massive clouds of gas and dark matter in the early universe could have directly collapsed to form black holes that are on the order of thousands of solar masses. Unlike typical stellar black holes, which form through the collapse of individual massive stars, these direct collapse black holes could create a sufficiently massive seed that would be capable of growing quickly through accretion of gas and mergers with other black holes. Another possibility is that supermassive black holes grew from a population of smaller black holes formed from the initial generations of stars. In this scenario, early stars could have been more massive than those typically formed today, exploding as supernova and leaving behind black holes. Over time, these smaller black holes could have merged with one another, accumulating mass and growing into supermassive black holes as they fed on gas falling into their vicinity. This growth process would have been enhanced in dense environments, such as in the centers of early galaxies, where gas was abundant. Cosmic evolution plays a crucial role in the scenario as well. The environment in which these black holes formed was teeming with gas left over from the Big Bang. This gas would have been ideal for powering the rapid accretion rates necessary for supermassive black hole growth. The interaction of dark matter and normal matter in these early dense regions would also contribute to the gravitational clumping that facilitated the birth of these massive entities. Currently, the detection of supermassive black holes in the early universe presents a rich field of study. Understanding their origins sheds light on galaxy formation and evolution, as supermassive black holes are closely tied to the dynamics of their host galaxies. This relationship ultimately influences the broader narrative of cosmic evolution, offering insights into how the universe transformed from the hot, dense state just after the Big Bang to the complex structures we observe today. Dark energy is a mysterious and fundamental component of the universe, comprising roughly 70% of the total energy density of the cosmos. Its nature remains one of the biggest enigmas in modern astrophysics. Dark energy is thought to be responsible for the observed accelerated expansion of the universe, a phenomenon that was first suggested in the late 90s when astronomers noticed that distant supernovae appeared fainter than expected, indicating that they were further away than previously believed. The leading explanation for dark energy is based on the concept of the cosmological constant, a term introduced by Albert Einstein in his equations of general relativity. In this framework, dark energy acts as a repulsive force that counterbalances the attractive force of gravity. This repulsion results in a consistent energy density filling space uniformly, exerting a negative pressure that drives galaxies apart over large distances. As the universe expands, the influence of dark energy becomes increasingly significant relative to the gravitational attraction of matter. Another hypothesis regarding the nature of dark energy involves dynamic fields, often referred to as quintessence. This idea posits that dark energy is not constant, but instead varies over time and space. Unlike the cosmological constant, which maintains a fixed energy density, quintessence involves a scalar field that evolves. This evolution could yield different effects on cosmic expansion as the energy density changes. Current observational data supports the presence of dark energy due to the accelerating expansion of the universe, as seen in the cosmic microwave background radiation, large-scale structure formation, and the behavior of distant supernovae. Understanding dark energy is critically important, as it plays a dominant role in shaping the ultimate fate of the universe. As investigations into its properties continue, astrophysicists aim to unravel the complexities of dark energy, hoping to clarify its nature and its profound impact on the evolution of the cosmos. Fast radio bursts, or FRBs, are intense bursts of radio waves that last only a few milliseconds, originating from distant galaxies. Despite their brevity, these events release an astonishing amount of energy, often comparable to the energy emitted by the sun over an entire day. The exact causes of FRBs remain largely enigmatic, but several theories have been proposed to explain their origins. One leading hypothesis suggests that FRBs may arise from neutron stars, particularly magnetars, which are highly magnetic neutron stars. During their violent activities, such as starquakes or magnetic reconnection events, these magnetars could emit powerful bursts that manifest as radio emissions. Some researchers also consider the possibility that FRBs could be generated by processes involving binary systems, stellar collisions, or even the collapse of massive stars into black holes. The study of FRBs offers valuable insights into the universe. Due to their extreme brightness across vast cosmic distances, FRBs can probe the intergalactic medium as their signals travel through space. By analyzing the dispersion measure, which reflects the number of free electrons along the path of the signal, scientists can glean information about the density of matter in the universe and the structure of the intergalactic medium. This information contributes to our understanding of cosmic evolution and the distribution of matter. Furthermore, the repeated detection of certain FRBs, such as the famous FRB 121102, raises intriguing possibilities. The ability to observe these bursts multiple times from the same source allows for more detailed studies of their environment and the conditions under which they are generated. As astronomers continue to uncover the origins and properties of fast radio bursts, they not only seek to answer the fundamental questions surrounding their formation, but also to utilize them as tools for exploring the underlying structure and dynamics of the universe. The observed flatness of the universe refers to the geometrical property of space where, on large scales, it appears to have a flat Euclidean geometry. This means that the rules of geometry we are familiar with, such as the sum of angles in a triangle equaling 180 degrees, hold true across vast distances. This flatness is significant because it has deep implications for cosmology and our understanding of the universe's fate. One of the key principles explaining the universe's flatness is the inflationary model. According to this theory, the universe underwent a rapid expansion in its earliest moments, shortly after the Big Bang. During this brief period known as cosmic inflation, the universe expanded exponentially, smoothing out any initial irregularities and fluctuations. This rapid expansion essentially stretched space to the point where any curvature was flattened, resulting in a geometry close to flat on large scales. Another important factor in understanding the flatness of the universe is the overall energy density associated with different components, such as matter, radiation, and dark energy. Observations indicate that the total energy density of the universe is remarkably close to the critical density, the precise threshold at which the universe is geometrically flat. If the density were greater than the critical density, the universe would be closed and curved like a sphere. Conversely, if the density were less, it would be open and have a hyperbolic geometry. Current measurements from the cosmic microwave background radiation and large-scale structure indicate that the universe's density is balanced very close to this critical value, further supporting the notion of flatness. Moreover, the dynamics driven by dark energy, which currently dominates the energy density of the universe, play a role in shaping its overall structure. As the universe expands, dark energy causes acceleration, which can influence the long-term geometry of space. The combination of these factors contributes to our understanding of why the universe appears flat and provides crucial insights into cosmic evolution and the balance of forces that govern the universe. Understanding flatness is essential not just for cosmological models, but also for predictions regarding the universe's ultimate fate and the mechanisms driving its expansion. Cosmic voids are vast, relatively empty regions of space that contain significantly fewer galaxies and matter than the average density of the universe. They can span from tens of millions to over 100 million light-years across, and are seen as one of the most intriguing features of the large-scale structure of the cosmos. These voids are surrounded by denser regions of galaxies known as galaxy clusters and superclusters, creating a web-like structure that scientists refer to as the cosmic web. The formation of cosmic voids is believed to be closely related to the gravitational dynamics of matter and the evolution of the universe. During the early universe, slight density fluctuations in the distribution of matter led to regions where galaxies and gas began to cluster together. Over time, gravity pulled matter into these denser regions while leaving larger gaps of space relatively empty, resulting in the formation of voids. As matter continued to clump and coalesce into filaments and sheets, the voids became more pronounced. Cosmic voids play a crucial role in our understanding of the universe's large-scale structure and dynamics. Observational studies show that these voids can influence galaxy formation and evolution, as their relatively low density alters gravitational interactions. They can affect how galaxies within denser regions behave and interact, potentially impacting the distribution of galaxies and related phenomena such as the growth of large-scale structures over time. Moreover, studying cosmic voids provides valuable information about dark matter and dark energy. As researchers analyze the distribution, size, and characteristics of voids, they can infer the underlying gravitational effects of dark matter that shapes the cosmic web. Understanding voids can also yield insights into the properties of dark energy, as the expansion of the universe influences the growth and formation of both voids and denser regions. This makes cosmic voids a fascinating subject in cosmology, contributing to our broader comprehension of the universe's structure, evolution, and the forces that govern its behavior. The cosmic microwave background, often referred to as the CMB, is the remnant radiation from the Big Bang, existing as a faint glow permeating the entire universe. This radiation is predominantly in the microwave part of the electromagnetic spectrum and has a nearly uniform temperature of about 2.7 degrees above absolute zero. The CMB provides a snapshot of the universe when it was just about 378,000 years old, shortly after the Big Bang, making it a crucial tool for understanding the early conditions of the cosmos. The significance of the CMB lies in its informative nature about the universe's infancy. When the universe cooled sufficiently, protons and electrons combined to form neutral hydrogen, allowing photons to travel freely without constant scattering. This moment, known as recombination, marks the release of the CMB, which carries information about the density fluctuations of matter and energy at that time. These fluctuations are believed to be the seeds of all current structures in the universe, such as galaxies and galaxy clusters. Detailed measurements of the CMB, particularly from satellites like the Wilkinson Microwave Anisotropy Probe and the Planck satellite, reveal tiny temperature variations or anisotropies that correspond to regions of different densities. Analyzing these variations allows scientists to glean insights into the composition of the early universe, including the proportions of ordinary matter, and dark energy. The data collected have provided strong evidence supporting the inflationary model of the universe, which describes a rapid expansion in the very early moments after the Big Bang. The CMB also serves as a compact cosmic history, illustrating how the universe evolved from a hot, dense state to its current expansive form. Through the study of the CMB, astronomers can refine models of cosmic evolution and gain a clearer understanding of fundamental cosmological parameters, including the Hubble constant, the age of the universe, and the overall geometry of space. Thus, the cosmic microwave background is a cornerstone of cosmology, unveiling the universe's earliest moments and aiding in our quest to understand its vast complexities. The matter-antimatter asymmetry in the observable universe refers to the puzzling observation that there is a significant excess of matter over antimatter. In theory, the Big Bang should have produced equal amounts of matter and antimatter. However, the universe we observe is dominated by ordinary matter, with very little antimatter present. This discrepancy raises fundamental questions about the fundamental laws of physics and the processes that occurred in the early universe. Several hypotheses have been proposed to explain this asymmetry, one of which involves a phenomenon known as baryogenesis. Baryogenesis refers to the processes that could have produced an imbalance between baryons, which are particles such as protons and neutrons, and antibaryons, their antimatter counterparts. For such processes to create an excess of matter, certain conditions must be satisfied, as described by the Sakharov conditions. There must be processes that violate baryon number conservation. There must be C and CP violation, which involve the symmetry between matter and antimatter, and the universe must experience non-equilibrium conditions conducive to creating a disparity. One well-studied candidate for baryogenesis involves the electroweak phase transition occurring at high temperatures shortly after the Big Bang. The dynamics of this phase transition may allow for CP violation, which would enable more matter production than antimatter. Other models propose mechanisms involving decays of heavy particles, such as the decay of certain supersymmetric particles, which could provide the necessary processes to yield an excess of baryons. In addition to these theoretical frameworks, researchers are exploring various experimental avenues to provide insights into the matter-antimatter asymmetry. For example, studies involving neutrinos and their interactions may reveal additional sources of CP violation and other phenomena that could help explain the observed imbalance. Precision measurements of particle interactions at high-energy particle accelerators also shed light on fundamental symmetries and can potentially uncover new physics beyond the standard model. Overall, the matter-antimatter asymmetry remains one of the most profound mysteries in cosmology and physics. As scientists continue to explore and test various hypotheses, they hope to unravel this compelling puzzle and deepen our understanding of the fundamental forces and events that shape the universe. Gravitational waves are ripples in the fabric of space-time produced by the acceleration of massive objects, particularly during dramatic astrophysical events. First predicted by Albert Einstein in his general theory of relativity, these waves propagate outward from their source at the speed of light. They occur when massive bodies, such as neutron stars or black holes, collide or merge, causing distortions in space-time that can stretch and compress the distances between objects. The detection of gravitational waves is made possible by highly sensitive instruments like the Laser Interferometer Gravitational Wave Observatory, or LIGO, and later the Virgo collaboration. These observatories measure minuscule changes in distance caused by passing gravitational waves, as they can cause fluctuations smaller than a fraction of the diameter of a proton. The first direct detection of gravitational waves in 2015 was a groundbreaking moment that confirmed Einstein's century-old prediction and opened a new chapter in observational astronomy. Gravitational waves provide unique insights into cosmic events that are otherwise difficult to observe. For example, they allow scientists to study the mergers of black holes and neutron stars, events that are often hidden from traditional electromagnetic observations. By analyzing the frequencies and amplitudes of these waves, researchers can deduce vital information about the properties of the merging bodies, such as their masses, spins, and distances from Earth. Moreover, gravitational wave astronomy has the potential to unveil previously unseen aspects of the universe, including the formation and evolution of compact astrophysical objects, the nature of neutron stars, and the behavior of matter under extreme conditions. When combined with electromagnetic observations, such as gamma rays and X-rays from the same events, gravitational waves enhance our understanding of the universe's most energetic processes and provide a more complete picture of cosmic phenomena. Overall, gravitational waves represent a revolutionary advancement in astronomy. They not only confirm decades of theoretical work, but also pave the way for exploring new realms of astrophysics, allowing scientists to probe the universe in ways that were previously unimaginable. The study of gravitational waves continues to evolve, promising to illuminate profound mysteries about the cosmos and the fundamental laws governing the universe. The cosmic web is a vast structure that outlines the organization of matter in the universe. It can be visualized as a network of interconnected filaments, nodes, and voids, which are composed of galaxies, galaxy clusters, and dark matter. This intricate web is formed due to the gravitational pull that influences how matter clumps together over billions of years, creating the large-scale structure that we observe in the cosmos. Throughout the universe, these filaments of galaxies stretch across immense distances, connecting vast clusters. They define the regions where galaxies reside, forming the hubs of activity in the universe. This arrangement is not random. It comes from the early conditions in the universe after the Big Bang, where tiny fluctuations in density laid the groundwork for the growth of structures over time. Gravity caused the matter to gather along these filamentary structures, while the vast empty spaces between them are referred to as voids, which can contain relatively few galaxies. What makes the cosmic web particularly fascinating is its scale and complexity. While our Milky Way galaxy might seem grand to us, it is just a tiny dot in this colossal structure. The observed shape and distribution of galaxies provide insights into fundamental questions about dark matter and dark energy, which together account for most of the universe's mass energy content. These concepts continue to challenge our understanding of physics and cosmology, as they represent the hidden components that shape the cosmos. Studying the cosmic web offers astronomers clues about the evolution of the universe, including the formation and interaction of galaxies. By mapping the arrangements of galaxies and searching for patterns, researchers are piecing together the mysterious history of the universe, unveiling how it reached its current state and where it may head in the future. Understanding the cosmic web not only informs us about the structure of the universe, but also deepens our appreciation of the forces that govern everything around us. Magnetars are a special type of neutron star, and they possess the most extraordinary magnetic fields known to exist in the universe. The key to understanding how these powerful magnetic fields are generated lies in the extreme conditions present during the formation of a neutron star and the unique properties of the matter within it. When a massive star exhausts its nuclear fuel, it undergoes a supernova explosion, leaving behind a core that collapses under its own gravity. This remnant becomes incredibly dense, compressing the material to the point that protons and electrons merge to form neutrons. As this neutron star forms, the conservation of angular momentum plays a significant role. If the original star had a substantial rotation speed, the neutron star will spin rapidly. During this process, the intense gravitational collapse generates enormous pressure, which leads to the alignment of particles and the amplification of magnetic fields. This mechanism is somewhat analogous to how spinning a figure skater pulls in their arms, leading to a faster rotation. In the dense environment of a neutron star, this rapid rotation coupled with the conductive properties of the neutron-rich matter enhances the magnetic field intensity. The magnetic fields of magnetars can reach strengths of over 1 billion teslas, which is more than 1,000 times stronger than the magnetic fields of regular neutron stars. The exact process that creates these exceptional magnetic fields is still a topic of active research, but it is believed that a dynamo effect occurs in the star's interior. This involves the motion of conducting fluids in the highly energetic and dense environment of the magnetar, creating electrical currents that further amplify the magnetic field. These immense fields are not static. They create complex dynamics within magnetars, resulting in phenomena such as starquakes, which release bursts of energy as the star's crust adjusts to the extreme magnetic forces. The resulting bursts of gamma rays and X-rays from these sudden releases lead to some of the most energetic events observed in the universe. Exploring magnetars helps astronomers unlock deeper insights into the nature of matter under extreme conditions, providing a glimpse into the fundamental laws governing our universe. Tabby's star, formerly known as Chi-C 846,285-2, has captured the fascination of astronomers and space enthusiasts alike due to its unusual and periodic dimming pattern. Discovered through observations from the Kepler Space Telescope, this star presented significant and unexplained variations in brightness, leading to numerous theories about what could be responsible for these fluctuations. Initially, one explanation suggested the presence of dust or debris clouds orbiting the star. As these clouds pass in front of Tabby's star, they would obscure some of its light, causing the observed dimming. However, the characteristics of the dimming did not align perfectly with what researchers would expect if it were solely due to dust. The irregular dips in brightness, varying in depth and duration, hinted at another more complex cause. One of the more intriguing hypotheses proposed that there might be an enormous structure around Tabby's star, potentially an alien megastructure, such as a Dyson sphere designed to harvest its energy. This speculative idea was met with excitement, although it remains highly unlikely. Subsequent observations have increasingly leaned towards more natural explanations, particularly involving objects like comets. A swarm of numerous comets could produce similar effects as they approach the star, creating temporary obscuration as they cluster and disintegrate. So far, no single explanation has fully resolved the mystery surrounding the periodic dimming of Tabby's star. Ongoing studies continue to explore its behavior, utilizing advanced monitoring techniques and potentially revealing new insights into the star's peculiar light curves. Each observation brings us closer to understanding not only Tabby's star, but also the diverse phenomena occurring in our universe. This case exemplifies how astronomical discoveries can challenge our understanding and spark both scientific inquiry and imagination. Binary star systems, which consist of two stars orbiting a common center of mass, are a prevalent feature in the cosmos. They form through processes that are intrinsically tied to the life cycle of stars and the conditions in stellar nurseries. When a molecular cloud collapses under its own gravity, it can fragment into multiple clumps. Each clump of gas begins to coalesce, forming protostars. If two of these protostars form close enough together, their mutual gravitational attraction can cause them to join in a binary system as they evolve. As stars develop, they may share material during their early stages, leading to a variety of mass ratios between the two stars. This interaction can also influence their subsequent evolution. For instance, if one star in a binary system becomes more massive, it may ascend to different evolutionary phases quicker than its companion, impacting the dynamics of the system significantly. Additionally, if the stars are very close, they can exchange mass through processes like Roche-Lobe overflow, where one star extends its outer envelope into the gravitational influence of its companion. The evolutionary paths of binary stars can vary widely. If one of the stars becomes a red giant, it can transfer mass to the other star, often leading to dramatic changes such as type Ia supernovae, where a white dwarf accumulates enough mass from its companion to ignite carbon fusion. Alternatively, these systems can produce phenomena like X-ray binaries, where in cases of mass transfer, the infalling material heats up and emits X-ray radiation as it spirals into the denser star. The fate of binaries also depends on their initial separation and masses. Wide binaries tend to evolve independently, while closer binaries can enter into more complex interactions. Eventually, as these stars age, they may lead to results such as one star becoming a white dwarf while the other continues to undergo its own evolution. The interconnected development of binary stars provides essential insights into stellar evolution and the diverse outcomes that can be observed in the universe, demonstrating the intricate relationships that govern stellar behavior. A star's life cycle is a fascinating journey that spans millions to billions of years depending on its mass. The process begins in a stellar nursery, where massive clouds of gas and dust collapse under their own gravity. As the material condenses, it forms a protostar, which gradually heats up due to the gravitational energy being converted into thermal energy. This critical phase involves the accumulation of mass, and when the protostar reaches a sufficient temperature and pressure at its core, nuclear fusion ignites, marking the transition to the main sequence stage. During the main sequence, which constitutes the bulk of a star's life, hydrogen nuclei fuse into helium, producing energy in the process. The duration of this phase varies according to the star's mass. Massive stars may only spend a few million years in this stage, while smaller stars like our Sun can remain for about 10 billion years. As hydrogen fuel gets depleted, the star begins to evolve. Its core contracts under gravitational pressure while the outer layers expand, transforming it into a red giant. Once a star reaches the red giant phase, its core temperature rises enough to allow for the fusion of helium into heavier elements, such as carbon and oxygen. However, not all stars follow the same path. The future pathways diverge based on their original masses. Low to medium mass stars like the Sun ultimately shed their outer layers, creating a stunning planetary nebula, while the core remains as a white dwarf, gradually cooling and fading over time. For high-mass stars, the story takes a more dramatic turn. When they exhaust their fuel, they undergo a series of fusion processes, forming increasingly heavier elements until they culminate in a core rich in iron. Eventually, when the core can no longer support itself under gravitational collapse, it triggers a supernova explosion. This spectacular event disperses the stellar material into space, enriching the interstellar medium and potentially forming new stars and planets. The remnant core can compress into an incredibly dense neutron star or even collapse further to become a black hole, marking the end of that star's life cycle while contributing to the cosmic narrative of creation and destruction. Supernovas are among the most spectacular events in the universe, marking the explosive death of stars. There are two primary types of supernovas, each arising from different mechanisms. Type 1 supernovas occur in binary star systems, where a white dwarf accumulates mass from a companion star. Once the white dwarf reaches a critical mass threshold, known as the Chandrasekhar limit, the pressure and temperature in the core become sufficient for carbon fusion to ignite rapidly. This runaway nuclear reaction leads to the destruction of the white dwarf in a cataclysmic explosion. On the other hand, Type II supernovas result from the life cycle of massive stars. When such stars exhaust their nuclear fuel, the fusion processes that balance gravitational collapse cease. As the star's core contracts under immense gravitational pressure, it forms a dense iron core. Eventually, once the core reaches a mass that exceeds its ability to resist gravity, it collapses, causing an explosive rebound effect that blasts the outer layers of the star into space. The shockwave from this violent explosion can outshine entire galaxies for a brief period, revealing the immense energy released during the event. Supernovas play a crucial role in cosmic evolution and the chemical enrichment of the universe. The elements formed in the cores of stars, as well as those created during the explosion, are dispersed throughout the interstellar medium. This material provides the building blocks for future stars, planets, and even life. Supernovas synthesize and scatter heavy elements, such as iron, nickel, and lead. Without these explosive events, the universe would be far less rich in diversity and complexity. The remnants of supernova explosions, often in the form of neutron stars or pulsars, also offer fascinating insights into astrophysics. The energetic bursts associated with supernovas can trigger the formation of new stars in nearby clouds of gas, influencing the structure and evolution of galaxies. In this way, supernovas are not merely ends, but also beginnings, contributing significantly to the dynamic tapestry of the universe. Through their powerful implications, these cosmic explosions remind us of the interconnectedness of stellar life cycles and the ongoing process of cosmic evolution. Neutron stars are incredibly dense remnants left behind after the explosive deaths of massive stars. Their formation occurs during supernova events, where the core of the star collapses under its own gravity, leading to the compression of protons and electrons into neutrons. This results in a star primarily composed of neutrons, with a mass greater than that of the Sun compressed into a sphere just a few kilometers across. Within the realm of neutron stars, several distinct types exist, each defined by unique characteristics and formation processes. One prominent type is the pulsar, a rotating neutron star that emits beams of electromagnetic radiation from its magnetic poles. As the pulsar spins, these beams sweep across space, and if they align with Earth, we detect them as regular pulses, much like a cosmic lighthouse. Pulsars form from neutron stars that retain significant rotation speeds after their progenitor stars explode. As the core collapses, the conservation of angular momentum causes the neutron star to spin rapidly, leading to the formation of strong magnetic fields. Another notable type is the magnetar, recognized for its extraordinarily powerful magnetic fields, which can be over 1 billion times stronger than those of typical neutron stars. Magnetars are created similarly to pulsars, but they have a more intense magnetic field due to the specific conditions of their formation. This can arise from the rapid rotation and the unique properties of the material within the magnetar during its collapse. The intense magnetic fields can lead to dramatic phenomena such as starquakes and explosive bursts of X-rays and gamma rays. In addition to these, there are also binary neutron stars, which are systems of two neutron stars orbiting each other. These can form both as a result of two stars evolving simultaneously in a binary system or through interactions that lead to the merger of neutron stars. Such mergers are significant events that can create heavy elements through processes like kilonovae, which enrich the universe with materials essential for planet formation and life. The diversity among neutron stars showcases the complex and varied outcomes of stellar evolution. Each type provides vital insights into the extremes of physical conditions and the fascinating processes that govern the life and death of stars in our universe. Understanding neutron stars not only deepens our knowledge of high-energy astrophysics, but also informs us about the cosmic processes that have shaped our galaxy over billions of years. White dwarfs are the remnants of medium-sized stars. specifically those that have exhausted their nuclear fuel after reaching the end of their stellar life cycles. The formation process begins when a star, like our Sun, evolves into a red giant after burning through its hydrogen. As it transitions, the core contracts while the outer layers expand dramatically. When the helium in the core begins fusing into heavier elements, the star enters a phase where it sheds its outer layers, creating a planetary nebula. What remains is the hot, dense core, which is ultimately the white dwarf. This core is primarily composed of carbon and oxygen, remnants of the star's earlier fusion processes. Unlike larger stars that explode as supernovas, the white dwarf gradually cools over time. The pressure of electron degeneracy, a quantum mechanical effect, provides the necessary support to prevent the white dwarf from collapsing under its own gravity, allowing it to exist as a stable object against gravitational collapse. Interestingly, a white dwarf's mass is limited. It can be no more than approximately 1.4 times that of the Sun, known as the Chandrasekhar limit. Exceeding this limit can lead to a supernova if it draws material from a companion star, turning it into a Type 1 supernova. The ultimate fate of a white dwarf is to continue cooling and fading over an incomprehensibly long timescale. Initially, it shines brightly due to residual thermal energy, but over billions of years this energy dissipates. As it cools, it becomes increasingly dimmer, transforming into a cold, dark remnant known as a black dwarf. However, this stage is theoretical, as the universe is not yet old enough for any white dwarf to have cooled to such a state since the formation of the first stars. White dwarfs play a significant role in the evolution of galaxies and the recycling of stellar material. As they cool, they contribute to the interstellar medium, allowing for the formation of new stars and planets over time. The process of a white dwarf's cooling and eventual transformation underscores the constant cycle of birth and death in the universe, illustrating how remnants of stars contribute to the ongoing evolution of cosmic matter. Stellar flares are sudden, intense bursts of energy that erupt from the surfaces of stars, including our own Sun. These phenomena are caused by the complex magnetic activity associated with stars. In particular, flares are linked to the dynamics of magnetic fields generated by the movement of electrically charged particles in the stellar atmosphere. As magnetic field lines become tangled due to the star's rotation and convection currents in its outer layers, they can snap and reconnect, releasing an enormous amount of energy. This energy release occurs in the form of electromagnetic radiation across the spectrum, ranging from radio waves to X-rays and gamma rays. The intense heat generated during a flare can lead to abrupt increases in brightness, making them detectable from significant distances. In the case of our Sun, solar flares are observed frequently and can vary in intensity, impacting space weather and conditions within the solar system. Nearby planets, including Earth, can be significantly affected by stellar flares. When a flare occurs, it releases particles, primarily electrons and protons, into space, creating what is known as a coronal mass ejection if the release is substantial enough. If these charged particles collide with a planet's magnetosphere, they can lead to geomagnetic storms. On Earth, these storms can disrupt satellite communications, affect power grids, and intensify auroras, resulting in beautiful light displays near the poles. For planets lacking strong magnetic fields, such as Mars, the impact is even more pronounced. These bodies are more vulnerable to the energetic particles, which can strip away their atmospheres over time, affecting their habitability and surface conditions. Studying stellar flares helps astronomers understand both the magnetic behavior of stars and their potential implications for any planetary systems in their vicinity, revealing the dynamic and sometimes hazardous nature of stellar environments. The effects of these flaring events provide valuable insights into how stars interact with the worlds that orbit them, shaping the evolution of planetary atmospheres and conditions for life. Pulsars are a fascinating type of neutron star known for their remarkably regular and periodic emissions of radio waves. The mechanism behind this pulsating signal stems from the unique physical characteristics of neutron stars, particularly their rotation and the presence of strong magnetic fields. When a massive star undergoes a supernova explosion, its core collapses into a neutron star, resulting in an incredibly dense and rapidly spinning object. As a pulsar spins, its strong magnetic field, which can be trillions of times stronger than Earth's, channels charged particles along its magnetic poles. These particles primarily consist of electrons, which are accelerated to nearly the speed of light. Because the magnetic field is tilted in relation to the rotation axis of the pulsar, the beams of radiation produced are not emitted uniformly, but rather concentrated in two opposing cones focused around the magnetic poles. As the star spins, these beams sweep across space, creating a directional signal much like a lighthouse beacon. If the beam of radiation aligns with Earth's line of sight, we detect the radio waves as pulses. The regularity of the signals is astonishing. Some pulsars can emit radiation with periods of milliseconds, while others might have periods ranging from seconds to minutes. The stability of these pulses is due in part to the well-defined rotational periods of pulsars, resulting from their conservation of angular momentum. There are also different types of pulsars. Millisecond pulsars, for example, are known for their incredibly fast rotation rates, occurring as they gain angular momentum by accreting material from a companion star in a binary system. This rapid spinning leads to extremely precise timing and regularity, making them valuable tools for testing theories of gravity, understanding the behavior of matter under extreme conditions, and even studying gravitational waves. The study of pulsars not only enhances our understanding of neutron stars and the physics of dense matter, but it also opens up intriguing questions regarding fundamental astrophysical processes. Each pulse serves as a reminder of the extraordinary conditions that govern neutron stars and the cosmic phenomena that arise from their unique features. Brown dwarfs are fascinating astronomical objects that occupy a unique position between the largest planets and the smallest stars. They form in stellar nurseries like other stellar objects, but they never acquire enough mass to initiate hydrogen fusion, the process that powers typical stars. Instead, they have a mass range that typically falls between about 13 and 70 times the mass of Jupiter, defining them distinctly from true stars and gas giant planets. The reason brown dwarfs are often referred to as failed stars lies in their inability to sustain hydrogen fusion in their cores. While a star like the Sun can maintain its equilibrium by fusing hydrogen into helium for billions of years, brown dwarfs lack the necessary mass and pressure to trigger this process. Instead, they may fuse deuterium, a heavier isotope of hydrogen, but only for a brief period beyond formation. As a result, brown dwarfs become cool and dim, radiating energy primarily in the infrared spectrum, making them difficult to detect with conventional optical telescopes. Brown dwarfs can also exhibit interesting characteristics. They have atmospheres that can include clouds of various compounds, such as water, ammonia, and even silicates, similar to those found in the atmospheres of gas giants. Their relatively cool temperatures allow for the presence of complex chemistry, and in some cases, they can exhibit weather patterns and cloud formations. Understanding brown dwarfs is essential for several reasons. They not only bridge the gap between stars and planets, but they also provide insight into the processes of stellar formation and the initial mass functions that govern the creation of celestial objects. Furthermore, studying brown dwarfs contributes to our broader understanding of cosmic evolution and the diversity of objects within our galaxy, indicating that the universe is filled with more than just stars and planets. As researchers continue to find and study these intriguing objects, they enhance our knowledge of the myriad forms that matter can take in the cosmos. Supermassive black holes, which can possess millions to billions of times the mass of our Sun, are typically found at the centers of galaxies, including our Milky Way. The formation of these enormous structures is a complex process that likely involves several overlapping mechanisms, which researchers are still working to fully understand. One leading theory suggests that supermassive black holes originate from the merging and growth of smaller black holes and other massive objects over cosmic time. Initially, the process starts with the formation of stellar black holes after the collapse of massive stars. These black holes can grow by accreting surrounding gas and dust from their environments and can merge with other black holes formed in the star clusters or during supernova events. This gradual accumulation of mass through accretion and mergers can cause these once relatively small black holes to grow significantly. Another critical factor in the formation of supermassive black holes is the behavior of matter in the early universe. Shortly after the Big Bang, dense regions of gas began to collapse, forming the first stars and clusters. Some of these primordial stars may have been incredibly massive and collapsed directly into black holes. The dense environments of early galaxies could facilitate rapid growth, where gas falls into the gravitational well and heats up, creating intense conditions for rapid accretion. Moreover, the interactions and mergers of galaxies contribute to the formation of supermassive black holes. When galaxies collide, their central black holes can also merge, leading to a final massive black hole. Such galactic mergers are common events in the evolutionary history of the universe. The gravitational dynamics during these encounters can funnel gas toward the center, further fueling the growth of the black hole. The presence of supermassive black holes at the centers of galaxies has profound implications for astrophysics and galaxy formation. They influence galaxy formation and evolution, affecting the motion of stars and the pattern of star formation within the galaxy. Understanding the formation and growth of supermassive black holes not only sheds light on the structure of galaxies, but also provides insights into the physics of gravity and the nature of space-time itself. As astronomers continue to explore this intriguing subject, they deepen our understanding of the dynamic processes that have shaped our universe over billions of years. The event horizon of a black hole marks a boundary beyond which nothing can escape the gravitational pull of the black hole, not even light. This critical threshold leads to intriguing questions about the nature of space-time and what happens to objects or information that cross it. Scientifically, it is challenging to understand precisely what occurs beyond the event horizon, since no information can return to be observed or measured from that region. Once an object crosses the event horizon, it is inexorably drawn toward the singularity, the core of the black hole where gravity becomes infinite, and the laws of physics as we know them begin to break down. The nature of the singularity itself remains one of the biggest mysteries in astrophysics. Theories suggest that as matter approaches the singularity, it would experience extreme tidal forces, resulting in spaghettification, where it gets stretched and compressed due to the intense gravitational gradient. Relativity suggests that from the perspective of an observer falling into a black hole, crossing the event horizon might not be an immediately catastrophic experience. They could pass through the horizon without noticing anything unusual, although their fate would be sealed as they approach the singularity. However, from the viewpoint of an outside observer, the infalling object appears to slow down and never quite crosses the event horizon due to the extreme time dilation effects of gravity. As the object approaches the horizon, light signals become increasingly red-shifted, eventually fading from view. The implications of what happens beyond the event horizon also touch upon significant theoretical concepts in physics, particularly concerning information loss. The information paradox challenges our understanding of quantum mechanics, as it raises the question of whether information that falls into a black hole is lost forever, or if it can be recovered in some form. Leading theories attempt to reconcile general relativity, which describes black holes classically, with quantum mechanics, suggesting that the information might be encoded on the event horizon itself or potentially preserved in other ways. While mysteries remain regarding the ultimate fate of matter and information inside a black hole, Ongoing research in areas like quantum gravity and black hole thermodynamics continues to provide insights. Each new discovery about black holes offers a window into the extreme conditions of the universe and the fundamental principles governing cosmic phenomena. Hawking radiation is a fascinating theoretical concept proposed by physicist Stephen Hawking, which suggests that black holes can emit radiation due to quantum mechanical effects near their event horizons. At first glance, this idea seems counterintuitive since black holes are known for their immense gravitational pull, which prevents anything from escaping once it crosses the event horizon. However, Hawking's analysis of the interplay between quantum mechanics and general relativity reveals a complex mechanism behind this radiation. The process begins with the concept of virtual particles, which are pairs of particles and antiparticles that spontaneously form and annihilate in empty space due to quantum fluctuations. According to quantum theory, these pairs can appear even in the vacuum near the event horizon of a black hole. Occasionally, one member of a particle-antiparticle pair can fall into the black hole while the other escapes into space. If this happens right at the moment of their creation, the escaping particle can be observed as radiation emanating from the black hole. For the escaping particle to become real and detectable as Hawking radiation, the particle that falls into the black hole effectively has negative energy from the perspective of an outside observer. This leads to a decrease in the black hole's mass as it loses some of its energy in the form of radiation. Over astronomical timescales, this continuous process implies that black holes can slowly lose mass and energy, potentially leading to their ultimate evaporation. However, the rate of Hawking radiation emission is incredibly low for large black holes, making it a negligible effect compared to their gravitational dominance. Hawking radiation plays an important role in theoretical discussions regarding the fate of black holes and the nature of information in the universe. The concept challenges our understanding of physics by raising profound questions about the preservation of information. If black holes lose mass and ultimately evaporate, what happens to the information about the matter that has fallen in remains an active area of research and debate. Overall, Hawking radiation represents a remarkable intersection of quantum mechanics and astrophysics, suggesting that black holes are not entirely black, but can emit radiation due to quantum effects. This insight continues to shape our understanding of black holes and the fundamental principles guiding the workings of the universe. The recent image of the black hole in the galaxy, M87, captured by the Event Horizon Telescope, marked a monumental milestone in astrophysics and our understanding of black holes. Released in April of 2019, this image provided the first direct visual evidence of a black hole's existence, offering unprecedented insight into these mysterious cosmic objects. The black hole in M87, which is estimated to be about 6.5 billion times the mass of the Sun, is located approximately 53 million light-years from Earth, making it a prime target for observation. The significance of this groundbreaking image lies not just in its visual confirmation of a black hole's existence, but also in the incredible technological and scientific collaboration involved in its creation. The Event Horizon Telescope is a global network of radio observatories that work together to create a virtual Earth-sized telescope. This cooperative effort involved thousands of scientists and spanning multiple countries, showcasing the power of global collaboration in advancing scientific knowledge. The image itself reveals a bright ring-like structure surrounding a dark central region, which corresponds to the black hole's event horizon. This striking representation aligns remarkably well with predictions from Einstein's theory of general relativity, providing further validation of this cornerstone of modern physics. The observation allows researchers to study the dynamics of matter as it spirals into the black hole and to explore fundamental questions about the nature of gravity, space-time, and how black holes interact with their surroundings. Moreover, the image of M87's black hole also has implications for our understanding of galaxy formation and evolution. Supermassive black holes like the one seen in M87 are often found at the centers of galaxies, and their growth can influence the structure and star formation within those galaxies. By examining such black holes, astronomers gain valuable insights into the processes that shape galaxies across the universe. This pioneering accomplishment not only marks a significant achievement in observational astrophysics, but also opens new avenues for future research. As technology improves and observation techniques advance, scientists hope to capture more detailed images of black holes, study their properties, and probe the mysteries of the universe they inhabit. The image of the black hole in M87 serves as both a scientific triumph and an inspiring reminder of the vast enigmas that still await discovery in the cosmos. Binary black hole systems evolve over time through intricate gravitational interactions. These systems typically begin when two massive stars orbit one another. After their life cycles end, both stars collapse, forming black holes. Over time, these black holes continue to orbit each other, gradually losing energy through the emission of gravitational waves. Gravitational waves are ripples in space-time that carry energy away from the system. As energy is lost, the black holes spiral closer together, accelerating their orbital motion. This phenomenon allows them to eventually draw near enough that their gravitational attraction becomes dominant, triggering the final stages of their merger. When the black holes approach each other at high speeds, they enter a phase known as the in-spiral. During this phase, they emit intense gravitational waves, which can be detected by observatories like LIGO and Virgo. The merger itself is a monumental event, producing a cataclysmic burst of energy as their event horizons combine, often creating a single, more massive black hole. After the merger, the newly formed black hole may oscillate for a brief period before settling into a stable state. The energy released during the merger is phenomenal, and the detection of such events has opened a new window into the study of the universe, allowing scientists to learn more about black holes and the fundamental laws of physics governing their behavior. Primordial black holes are intriguing cosmic objects that are believed to have formed in the very early universe, shortly after the Big Bang. Unlike the more familiar black holes that result from the collapse of massive stars, primordial black holes could have originated from density fluctuations in the hot, dense matter of the early universe. These fluctuations created regions where mass concentrated enough for gravitational forces to lead to instantaneous collapse. Various theories suggest that these black holes might have formed when the temperature of the universe was incredibly high, allowing for rapid gravitational collapse under certain conditions. As the universe expanded and cooled, regions with high density could have collapsed into black holes without any stars having to form first. This means that primordial black holes could range in size from tiny ones, with masses less than that of a typical asteroid, to much larger ones, potentially many times the mass of our Sun. Understanding primordial black holes has important implications for cosmology and dark matter research. Some theories propose that these black holes could make up a significant fraction of dark matter, which comprises a large portion of the universe's total mass, yet remains largely undetectable through traditional methods. Detecting primordial black holes or their effects could provide key insights into the fundamental processes that shape the universe and might even elucidate the nature of dark matter itself. As researchers continue to explore this fascinating topic, the quest to identify primordial black holes evokes essential questions about the conditions that existed at the dawn of time and how they have shaped the cosmos we observe today. Intermediate mass black holes serve as a fascinating bridge in our understanding of black hole evolution, occupying a mass range between stellar black holes, which are typically up to a few tens of solar masses, and supermassive black holes, which can reach millions or even billions of times the mass of our Sun. These intriguing objects generally have masses between 100 and 1,000 solar masses, and their existence challenges some long-standing theories about black hole formation. The formation of intermediate mass black holes is less understood. One hypothesis suggests they might arise from the mergers of smaller black holes in dense stellar environments, such as globular clusters. As stellar black holes collide and merge, they can accumulate mass, leading to the formation of intermediate mass black holes. Another possibility is that they form directly from the collapse of massive stars, possibly during the early phases of the universe when conditions allowed for more massive progenitor stars to exist. The study of these black holes is critical for understanding the growth of supermassive black holes found at the centers of galaxies. It is believed that intermediate mass black holes could act as seeds for supermassive black hole formation through further accretion of matter and additional mergers. Investigating their properties and distributions helps scientists piece together how black holes grew over cosmic time, revealing insights into galaxy formation and evolution. Observational efforts to detect intermediate mass black holes are ongoing, as traditional techniques may struggle with their elusive nature. Identifying these objects could not only confirm their existence but also illuminate the processes that govern black hole evolution and the roles they play in the cosmic landscape. The relationship between black holes and the formation of galaxies is a dynamic interaction that shapes the structure and evolution of the universe. At the core of many galaxies lies a supermassive black hole with masses ranging from millions to billions of times that of the Sun. These black holes influence the surrounding environment in profound ways, contributing to the growth and stabilization of galaxies over cosmic time. As galaxies form from vast clouds of gas and dark matter, the initial gravitational collapse leads to the creation of stars and other celestial bodies. During this process, matter can accumulate in the center of the nascent galaxy, forming a massive black hole through either the direct collapse of a gas cloud or the mergers of smaller black holes. This supermassive black hole plays a pivotal role in regulating the dynamics of the galaxy. The gravitational pull of the black hole affects the orbits of stars and gas within the galaxy, contributing to its overall structure. Additionally, the energy output from the supermassive black hole, particularly when it is actively accreting material, can drive powerful winds and outflows of gas. This feedback mechanism can either promote or inhibit star formation in the surrounding area, determining how the galaxy evolves. Research into the correlation between the masses of supermassive black holes and the stars in their host galaxies reveals a striking relationship. Observations indicate that more massive black holes are typically found in more massive galaxies, suggesting that the growth of black holes and galaxies is intertwined. This connection enhances our understanding of cosmic evolution, highlighting the significant role that black holes play in shaping not just galaxies, but the broader structure of the universe itself. Black holes profoundly impact both time and space in their vicinity due to the effects of their immense gravitational pull. According to Albert Einstein's theory of general relativity, massive objects warp the fabric of space-time. Black holes, being among the most dense and massive objects in the universe, create intense gravitational fields that cause significant curvature in this fabric. As one approaches the event horizon, the boundary beyond which nothing can escape a black hole's grasp, time appears to slow down relative to an outside observer. This phenomenon, known as time dilation, results from the black hole's gravitational influence. For someone near the event horizon, time would pass normally, but if they could somehow observe an outside clock, they would see it ticking much faster. This mind-bending aspect of black holes raises intriguing questions about the nature of reality and how we perceive time. Space itself is altered as well. The gravitational pull of a black hole creates a profound distortion, meaning that the paths taken by objects nearby are no longer straight lines. Instead, these paths curve around the black hole, which can lead to fascinating processes such as accretion disks, where material spirals rapidly into the black hole, heating up and emitting intense radiation. This curvature of space can affect the movement of stars and gas in nearby galaxies, influencing their dynamics. Moreover, the closer one gets to a black hole, the more extreme these effects become. At the singularity, the point at the center of a black hole where density becomes infinite, the known laws of physics break down, leaving scientists pondering the true nature of space, time, and gravity. Understanding how black holes manipulate time and space not only deepens our knowledge of these enigmatic objects, but also challenges and enriches our comprehension of the universe itself. During a black hole merger, two black holes in a binary system spiral towards each other, culminating in a dramatic collision that results in a single, more massive black hole. The merger process is marked by an incredible release of energy, primarily in the form of gravitational waves, which are ripples in the fabric of space-time caused by the acceleration of massive objects. As the two black holes approach one another, they enter a phase known as in-spiral. During this phase, they rapidly orbit around a common center of mass, gradually losing energy through the emission of gravitational waves. The closer they get, the more intense the waves become, creating a final burst of energy just before the merger. When the black holes collide, the event is characterized by a rapid coalescence, resulting in a single black hole. This newly formed black hole may oscillate briefly before settling into a stable state. Detecting these massive events is achieved using highly sensitive observatories like LIGO and Virgo, which are designed to measure the minute distortions in space-time created by passing gravitational waves. These facilities employ laser interferometry to detect changes in the lengths of arms that form an L shape. When a gravitational wave passes through, it stretches one arm while compressing the other, causing a detectable shift in the measurement. This technology allows scientists to observe distant black hole mergers and gain insights into their properties, such as masses and spin. The detection of gravitational waves not only confirms the existence of black hole mergers, but also opens new avenues for understanding fundamental physics, cosmology, and the nature of the universe. Each detected event provides valuable data, contributing to our understanding of how black holes form, merge, and evolve, while also offering glimpses into the early universe and the extreme nature of space-time around these colossal objects. The formation of the first stars and galaxies after the Big Bang is a pivotal era in cosmic history known as the Cosmic Dawn. In the first few moments following the Big Bang, the universe was a hot, dense soup of fundamental particles. As it expanded and cooled, protons, neutrons, and electrons formed, later combining to create simple atomic nuclei. This period, known as recombination, allowed electrons to bond with these nuclei to form neutral hydrogen and helium atoms. Once the universe became transparent to radiation, it entered the cosmic dark ages, a time when very little structure existed and the universe was predominantly filled with hydrogen and helium gas. Over hundreds of millions of years, tiny fluctuations in density caused by quantum effects in the early universe led to regions where matter began to clump together under the influence of gravity. As these regions contracted, they gathered mass, forming dense clouds of gas. Eventually, these clouds of hydrogen and helium became so dense and hot that nuclear fusion ignited, giving birth to the very first stars, known as population 3 stars. These stars were likely massive, and their enormous energy output led to the formation of heavier elements through nuclear fusion within their cores. Once burning their fuel quickly, these massive stars ended their life cycles in spectacular supernova explosions, dispersing these newly formed elements into the surrounding gas. The remnants of these explosions contributed to the gravitational collapse of nearby gas clouds, fueling the formation of the first galaxies. Over time, gravity brought together stars, gas, and dark matter into larger structures, leading to more complex galaxies. This critical process set the stage for the rich tapestry of the universe that we observe today, with galaxies evolving over billions of years through mergers, star formation, and the interplay of dark matter and cosmic expansion. Understanding this early formation phase enhances our knowledge of the universe's history and the processes that continue to shape it. Dark matter plays a vital role in the formation and evolution of cosmic structures in the universe. Unlike ordinary matter, which makes up stars, planets, and living beings, dark matter does not interact with electromagnetic forces, meaning it does not emit, absorb, or reflect light. This invisibility makes dark matter challenging to detect directly, but its presence is inferred through gravitational effects on visible matter, radiation, and the overall structure of the universe. Less than 1 billion years after the Big Bang, the universe was filled with a uniform distribution of gas and dark matter. As gravity began to pull this matter together, dark matter acted as a scaffold, influencing the clumping of ordinary matter. The gravitational wells created by dark matter allowed gas and dust to collapse into denser regions, leading to the formation of stars and galaxies. Essentially, while ordinary matter formed the visible structures of stars and galaxies, dark matter provided the framework that guided their growth. Galaxies form in halos of dark matter that provide the gravitational pull necessary to prevent the gas from dispersing. This dark matter halo is crucial for holding galaxies together, especially during interactions and mergers when galaxies collide. Observations of the rotation curves of spiral galaxies show that stars at the edges of galaxies move faster than they should if only visible matter were present. This disparity strongly suggests a significant amount of unseen dark matter in and around galaxies. The influence of dark matter extends on larger scales as well. It plays a crucial role in the formation of galaxy clusters and cosmic filaments, generating the large-scale structure we observe in the universe today. Dark matter acts like a network of highways, guiding the flow of matter in the cosmos. As research continues to investigate its properties and behavior, dark matter remains one of the most significant and mysterious components of our universe, essential to understanding cosmic structure formation and the fundamental workings of gravitational interactions. The rate of star formation has experienced significant changes throughout cosmic history, displaying a dynamic trajectory since the early universe. Initially, after the Big Bang, star formation was a slow process as the universe transitioned from a hot, dense state to a cooler, more structured one. For the first few 100 million years, the formation of stars was limited as the universe entered what is known as the cosmic dark ages, primarily composed of hydrogen and helium gas. As time progressed, approximately 1 billion years after the Big Bang, the formation of the first stars ignited a dramatic increase in the rate of star formation. This relationship is often referred to as the cosmic noon, a period roughly between 6 to 10 billion years ago when star formation peaked. During this era, galaxies were more abundant, and conditions were favorable for gas to collapse into stars, leading to the formation of massive populations of stars. The growth of massive galaxies also corresponded with frantic bursts of star formation activity during galaxy mergers and interactions. However, as the universe continued to expand and evolve, the rate of star formation began to decline. By about 5 billion years ago, this trend became more evident. Factors such as increased metal enrichment from supernova explosions and the regulation of star formation due to energetic feedback from massive stars contributed to this decline. As galaxies aged, their gas reservoirs gradually diminished, reducing the material available for new stars, and thus the overall star formation rate continued to decrease. Today, in the present age of the universe, star formation occurs at a much lower rate compared to its peak. The available gas in galaxies has been largely converted into stars, and with less gas to fuel further star formation, the universe is transitioning into a quieter phase. Observations suggest that while some galaxies still experience bursts of star formation, the overall trend points to a gradual aging of the universe as existing stars finish their life cycles. This evolving landscape of star formation illustrates the interconnectedness of cosmic processes and the dynamic nature of the universe over billions of years. The future of the universe, as outlined by current cosmological models, is shaped by several key factors, including the rate of expansion driven by dark energy, the distribution of matter, and the geometry of the universe. One prominent model, the lambda cold dark matter model, suggests that the universe is expanding at an accelerating rate due to dark energy, which makes up about 70% of the universe's total energy density. As this expansion continues, distant galaxies will drift further away from each other. In the distant future, millions to billions of years down the line, many galaxies will recede beyond the observable horizon, becoming unreachable and invisible to us. This gradual separation will lead to an effect known as cosmic isolation, where the visible universe becomes increasingly empty, dominated by the remnants of stars and galaxies that once flourished. Over an even longer timescale, the fate of existing stars comes into play. Most stars will exhaust their nuclear fuel eventually, leading to a universe filled with white dwarfs, neutron stars, and black holes. The death of stars will culminate in a dark cosmos, with only the faint glow of these remnants illuminating the void. In about 100 trillion years, it is suggested that star formation will cease, marking the end of an era for active galaxies. Looking further ahead on the scale of trillions of years, theories such as the heat death of the universe propose that entropy will continue to rise, leading to a state where the universe reaches thermodynamic equilibrium. In this scenario, galaxies, stars, and black holes will eventually decay into low-energy particles and radiation, resulting in a cold, dark, and sparsely populated universe. Ultimately, the future of the universe, as we understand it today, seems to be a long, gradual decline into obscurity, an infinite stretch of time characterized by silence and an absence of significant cosmic events. Galaxy clusters evolve through a complex interplay of gravitational interactions, merging, and the dynamics of their constituent galaxies and dark matter. These massive structures, which contain hundreds to thousands of galaxies bound together by gravity, serve as important laboratories for studying cosmic evolution. Initially, galaxy clusters began to form when small fluctuations in the density of matter in the early universe led to the gravitational collapse of regions filled with dark matter and gas. Over billions of years, these regions coalesced to create larger clumps, attracting nearby galaxies and matter through their gravitational influences. As galaxies fall into clusters, they often collide and merge, exchanging stars and gas in the process. This can trigger bursts of star formation as gas is compressed during interactions, leading to periods of elevated activity within the cluster. As clusters age, they continue to evolve through a process known as hierarchical clustering. Smaller groups and clusters merge to form ever larger ones, reshaping the galaxy population in the process. This merging activity can cause disruptions in galaxy morphology, transforming spiral galaxies into elliptical ones as collisions and interactions lead to the amalgamation of stars. The gravitational forces also influence the distribution of dark matter within the cluster, creating a gravitational potential well that affects the motion of galaxies. Furthermore, the intergalactic medium within these clusters is filled with hot, X-ray emitting gas, which plays a critical role in their evolution. As galaxies fall into the cluster, their gas can be stripped away, while the hot gas can provide thermal pressure that helps prevent further star formation. Over time, the energy dynamics, as well as feedback from active supermassive black holes at the centers of some galaxies, can regulate star formation and affect the overall growth and diversity of galaxies within clusters. In the long term, galaxy clusters will continue to change. They will eventually reach a point where the frequency of mergers declines, leading to a more stable configuration. Eventually, interactions will give way to a future where clusters are influenced primarily by dark energy, resulting in a gradual loosening of the structures as the universe expands. The interplay of gravity and dark energy ultimately dictates the fate of galaxy clusters and their evolution across cosmic timescales, providing essential insights into the history of the universe. The cosmic web is a fundamental aspect of the large-scale structure of the universe, representing the intricate arrangement of galaxies, galaxy clusters, and intergalactic matter. It resembles a vast network of filaments and voids, with galaxies located along these filaments that connect in a web-like pattern. This structure is a crucial element in understanding how matter is distributed throughout the universe and sheds light on the mechanisms that govern cosmic evolution. The cosmic web is primarily shaped by the gravitational influence of dark matter. Early in the universe's history, small fluctuations in density led to the gravitational collapse of dark matter, creating the framework of the cosmic web. Over billions of years, normal matter accumulated within these dark matter filaments, forming galaxies and clusters of galaxies. This process initiated a cycle of growth and merging that continues to influence the distribution of matter at large scales. In addition to housing galaxies, the cosmic web contains vast voids, regions where few galaxies exist. The existence of these voids is significant as they represent the areas where matter is less densely packed, contrasting sharply with the filaments that are teeming with galaxies. This stark variation highlights the role that the cosmic web plays in shaping galaxy formation and evolution, as the gravitational pull from the filaments affects how gas and dark matter concentrate to create new stars and galaxies. The study of the cosmic web provides important insights into large-scale cosmic phenomena. It allows researchers to trace the evolution of the universe and understand how it developed from a nearly homogeneous state to its current complex structure. Observations of the cosmic web, such as those made by large telescopes and surveys, also aid in exploring the fundamental properties of dark matter and dark energy, revealing deeper insights into the forces that shape our universe. Ultimately, the cosmic web is a vital framework for understanding the organization and evolution of cosmic structures on the grandest scales. Measuring the age and size of the observable universe involves a combination of cosmological observations, principles, and complex calculations. The age of the universe is primarily determined through the study of cosmic expansion and the behavior of distant galaxies. The key to this understanding comes from the observation that galaxies are moving away from us, and the farther they are, the faster they recede. This relationship is encapsulated in Hubble's law, which states that the velocity of a galaxy is proportional to its distance from us. To estimate the age of the universe, scientists analyze the cosmic microwave background radiation, which is the afterglow of the Big Bang. By measuring tiny fluctuations in this radiation, captured by observatories like the Wilkinson Microwave Anisotropy Probe and the Planck satellite, researchers can derive essential information about the universe's expansion history. When combined with measurements of the expansion rate, termed the Hubble constant, this data allows cosmologists to extrapolate backward, calculating how long ago the universe began to expand from an initial singularity. Current estimates place the age of the universe at approximately 13.8 billion years. On the other hand, determining the size of the observable universe is more about understanding how far light has traveled since the Big Bang. The observable universe is defined as the region from which light has had time to reach us since the beginning of cosmic expansion. Because light travels at a finite speed, the further away an object is, the longer its light takes to arrive. The observable universe is thus thought to extend about 46.5 billion light-years in all directions from our vantage point on Earth, giving it an overall diameter of around 93 billion light-years. The size is also influenced by the ongoing expansion of the universe. Since the Big Bang, space itself has expanded, meaning that the actual distance we measure today is greater than the distance light would have traveled in a static universe over the same time period. These measurements incorporate a variety of observational techniques, including supernovae observations and galaxy surveys, to provide a coherent picture of the cosmos and its vast extent. Together, the age and size measurements of the observable universe highlight the immense scale and history of our cosmic home. The evidence for the accelerating expansion of the universe primarily comes from observations of distant supernovae, as well as measurements of cosmic microwave background radiation and large-scale galaxy distributions. The key discovery that revealed this unexpected acceleration was made in the late 1990s when two independent teams of astronomers were studying type Ia supernovae, which are exceptionally bright and can be used as standard candles for measuring cosmic distances. When analyzing the light curves of these distant supernovae, researchers discovered that they were dimmer than expected based on previous models of a uniformly expanding universe. This dimming indicated that the supernovae were farther away than they should have been if the expansion had been slowing down over time. The data suggested that instead of a decelerating expansion due to gravitational attraction, the universe's expansion is accelerating, which led to the conclusion that an unknown form of energy was causing this phenomenon. This mysterious energy, termed dark energy, is believed to comprise approximately 70% of the universe's total energy density. Its nature remains one of the greatest enigmas in modern cosmology, but its influence on the expansion of the universe is evident. Further evidence supporting the accelerating expansion comes from observations of the cosmic microwave background radiation, which show how matter was distributed in the early universe and supports models consistent with an accelerating expansion. Additionally, galaxy surveys and observations of the large-scale structure of the universe have provided more insights into this phenomenon. Studies of galaxy clusters and their distribution over time reveal patterns that align with an accelerating universe influenced by dark energy. Collectively, these observations have transformed our understanding of the universe, revealing that not only is it expanding, but it is doing so at an increasing rate, challenging our conceptions of gravity and prompting research into the fundamental nature of dark energy. Cosmic voids are vast, relatively empty regions of space that are sparsely populated with galaxies, representing one of the most significant features of the large-scale structure of the universe. The formation of these voids is intricately linked to the gravitational dynamics of dark matter and the early developmental stages of the universe. In the aftermath of the Big Bang, the universe was nearly uniform but contained slight fluctuations in density. Over time, gravity began to pull matter together, creating denser regions that eventually formed galaxies and galaxy clusters. As matter accumulated in these denser areas, the surrounding regions experienced lower gravitational attraction. This led to the formation of voids, which are essentially the areas that did not accumulate enough matter to become dense enough to form galaxies. These voids grow larger as structures develop in the universe, reflecting the uneven distribution of matter throughout cosmic history. Voids evolve as a result of the ongoing processes of cosmic expansion and the interactions between galaxies and dark matter. As galaxies within clusters merge and develop, the gravitational influence of the clustered matter continues to pull material from the voids, further enhancing their emptiness. This process is known as the chimney effect, where the stable, low-density regions allow for the surrounding matter to be funneled into higher density areas, making voids more pronounced over time. The dynamics within voids can also influence galaxy formation and evolution. Galaxies located within voids often exhibit different characteristics, such as irregular shapes and lower star formation rates compared to those in denser environments. Furthermore, observations indicate that galaxies in voids may be less clustered, suggesting a more dispersed cosmic evolution. Cosmic voids form and evolve through the interplay of gravitational forces, the growth of structure, and the distribution of dark matter. Their presence not only marks the vast emptiness in the universe, but also provides essential clues about the processes governing the formation and behavior of galaxies in a continually expanding cosmic landscape. Magnetic fields play a crucial role in shaping cosmic structures, influencing everything from the formation of galaxies to the dynamics of stellar objects. They are present throughout the universe, embedded in interstellar and intergalactic mediums. The origins of these magnetic fields are still a subject of active research, but they are thought to arise from processes in the early universe and the movement of charged particles. As galaxies form and evolve, magnetic fields contribute to their overall structure and stability. They affect the behavior of gas and dust, which are the primary materials for star formation. When gas clouds collapse under gravity to form stars, magnetic fields can help regulate this process by providing additional pressure. This interaction can either enhance or inhibit star formation, leading to a more complex cosmic architecture. Beyond galaxies, magnetic fields extend into galaxy clusters, influencing the movement of plasma, which is a hot ionized state of matter. Interactions between charged particles in the plasma and magnetic fields can create various phenomena such as radio waves, contributing to our understanding of the universe. The presence of these magnetic fields can also guide cosmic rays, high-energy particles that travel through the universe at nearly the speed of light, shaping the behavior of these fast-moving entities as they traverse vast distances. Magnetic fields are integral to the intricate tapestry of cosmic structures. They govern not only the formation and stability of galaxies, but also play a vital role in the behavior of matter at the largest scales. As telescopes continue to probe deeper into space, the understanding of how these invisible forces interact with visible matter will undoubtedly evolve, revealing even more about the universe's complex makeup. Astronomers utilize several ingenious methods to detect exoplanets, which are planets orbiting stars outside our solar system. One of the most prominent techniques is the transit method, where astronomers look for slight dips in a star's brightness. When an exoplanet passes in front of its host star from our viewpoint on Earth, it temporarily blocks a fraction of the star's light. By monitoring these changes in brightness over time, astronomers can infer the size of the planet and its orbital period. Another popular method is the radial velocity technique, often referred to as the Doppler method. This approach relies on the gravitational effects that a planet exerts on its star. As a planet orbits, it causes the star to wobble slightly due to their mutual gravitational attraction. This wobble can be detected through shifts in the star's light spectrum. When the star moves toward us, its light appears slightly blue-shifted, and when it moves away, it becomes red-shifted. By measuring these shifts, astronomers can determine the presence of a planet and its mass. Direct imaging is another fascinating technique, although it is more challenging due to the brightness of stars overshadowing their planets. Astronomers utilize advanced technologies such as coronagraphy and adaptive optics to block out the starlight while capturing the light reflected or emitted by the exoplanet. This method is especially useful for observing large planets located far from their stars, providing insights into their atmospheres and potential habitability. Gravitational microlensing is a more recent method that takes advantage of the bending of light around massive objects, such as stars. When a foreground star passes in front of a more distant star, its gravity can magnify the distant star's light. If the foreground star has an exoplanet, distinct features appear in the light curve, indicating the presence of the planet. This technique allows astronomers to detect planets that are otherwise too faint or distant to observe using other methods. As technology advances, these techniques will continue to evolve, enhancing our ability to explore the universe's diverse array of worlds. Determining the potential habitability of exoplanets involves a comprehensive analysis of various environmental factors that could support life as we know it. One of the primary criteria for habitability is the concept of the habitable zone, often referred to as the Goldilocks zone. This zone is the region around a star where conditions may be just right for liquid water to exist on the surface of a planet. Since water is essential for life, identifying exoplanets within this zone is a crucial step in assessing their potential for supporting life. Beyond location, the composition of an exoplanet's atmosphere plays a significant role in its habitability. Astronomers study the atmospheric gases that could provide a stable climate capable of maintaining liquid water. Data about the presence of molecules such as carbon dioxide, oxygen, and methane can offer insights into the planet's possible biosignatures. Instruments on spacecraft and ground observatories analyze light spectra to detect these gases, giving scientists clues about the planet's atmospheric conditions and any processes that may indicate biological activity. Geological features also contribute to our understanding of habitability. For instance, the presence of plate tectonics can facilitate the recycling of nutrients and contribute to a dynamic climate, which may be favorable for life. Evaluating a planet's surface conditions, such as its temperature, pressure, and geological activity, helps scientists predict whether those conditions could support the development of living organisms. Moreover, recent advances in astrobiology have prompted researchers to consider alternative forms of life that may not depend on water as we know it. For instance, some hypotheses explore the potential for life based on ammonia or even silicon. As the search for exoplanets continues with sophisticated technology, our understanding of habitability might expand to include a broader range of environments, thereby enhancing our quest to find life beyond Earth. Several exoplanets have emerged as the most promising candidates for potential life as we know it. Among the most notable is Proxima Centauri b, which orbits the red dwarf star Proxima Centauri, our closest stellar neighbor. Located within the habitable zone, this planet has conditions that could allow for liquid water to exist on its surface. However, its proximity to a flare-active star raises questions about its atmospheric retention and long-term habitability. Another intriguing contender is Kepler 186f, located in the Kepler 186 system. This exoplanet is the first Earth-sized planet discovered within the habitable zone of a star similar to our Sun. Its size and position suggest that it may have the right conditions for liquid water, making it an exciting target for further study. Observations of its atmosphere and surface conditions could clarify its potential for supporting life. Then there is TRAPPIST-1, a system featuring 7 Earth-sized exoplanets orbiting a cool dwarf star. 3 of these planets fall squarely within the star's habitable zone, meaning they might possess temperatures conducive to liquid water. The diversity of these planets opens up numerous possibilities for studying different environmental conditions, which could enhance our understanding of habitability and the factors that support life. Lastly, LHS 1140b is another significant exoplanet that captured scientists' interest. This super-Earth is located in the habitable zone of its star and has a substantial size, which may indicate a thicker atmosphere and greater potential for retaining heat. Furthermore, its relatively close proximity to Earth allows for more detailed observations using current and upcoming telescopes. Each of these exoplanets presents unique opportunities for studying the conditions conducive to life and pushing the boundaries of our understanding of what can support biological activity in the universe. Exoplanetary systems exhibit a remarkable variety compared to our solar system, showcasing a diversity in planetary types, orbits, and dynamics that challenges our understanding of planetary formation. One of the most striking differences is the prevalence of hot Jupiters, which are gas giants that orbit very close to their host stars. In contrast, our solar system's gas giants like Jupiter and Saturn are located much farther away from the Sun. These close-orbiting gas giants have likely migrated inward over time due to gravitational interactions, changing our expectations about the stability of planetary orbits. Additionally, the arrangement of planets in many exoplanetary systems can differ significantly from the patterns observed in our own solar system. Some systems have been found to possess multiple planets in tight orbits, leading to configurations that are much more compact than our solar system's more spacious arrangement. In some cases, researchers have observed systems with closely packed planets that exhibit resonant orbits, where the gravitational interactions between them create a rhythmic pattern of movement. Such arrangements can lead to dynamic interactions not commonly seen among the planets in our solar system. The composition of exoplanets also varies widely. While our solar system contains terrestrial planets like Earth and Mars and gas giants, many detected exoplanets, particularly super-Earths and mini-Neptunes, differ in size and atmospheric characteristics. These planets can have unique features, such as thick hydrogen-helium atmospheres or rocky compositions, which do not directly correspond with any of the planets in our solar system. Such variability allows researchers to explore new hypotheses about planetary formation and the factors influencing planetary development. Lastly, the prevalence of planetary systems around various types of stars adds another layer of diversity. Many exoplanetary systems are found around M-type red dwarfs, which are abundant in the galaxy but possess different temperatures and luminosities compared to our Sun. This variance affects the habitable zones and potential climates of the planets orbiting these stars. By studying these differences, scientists can uncover essential insights into the processes that shape planetary systems and the potential for life beyond Earth. The Fermi paradox highlights the apparent contradiction between the high likelihood of extraterrestrial civilizations existing in the universe and the lack of evidence for or contact with such civilizations. Named after the physicist Enrico Fermi, the paradox is often encapsulated in the question, where is everybody? Given the estimated billions of potentially habitable planets in our galaxy alone, one might expect that we should have encountered signs of intelligent life by now. Yet, despite decades of searching, we have found no definitive evidence. Several proposed solutions attempt to explain this paradox. One possibility is that intelligent life is exceedingly rare in the universe. Although many planets may have suitable conditions for life, the transition from simple to complex organisms, and ultimately to advanced civilizations, could be a unique occurrence or an extremely rare event in cosmic history. This idea suggests that while microbial life might be common, technologically advanced civilizations could be sparse. Another solution posits that advanced civilizations tend to self-destruct before reaching a stage where they can communicate across the cosmos. This concept, often termed the Great Filter, suggests that there are significant challenges or catastrophic events, such as nuclear war, environmental collapse, or technological disasters, that prevent civilizations from lasting long enough to explore or colonize the galaxy. If this filter occurs at various stages of a civilization's development, it could explain the silence we observe. Alternatively, some theorists propose that advanced extraterrestrial civilizations exist, but actively choose not to make contact with humanity. This could be due to a variety of reasons, including the desire to avoid interference with less advanced civilizations, or the belief that revealing their presence would disrupt the natural development of emerging species. This speculative stance aligns with concepts like the prime directive in science fiction, suggesting a kind of cosmic ethical code preventing contact with less advanced life forms. Lastly, some hypotheses suggest that we might be overlooking the signs of extraterrestrial life entirely. Advanced civilizations may use technologies or methods of communication that we have not yet developed the capacity to detect. It is also possible that extraterrestrial civilizations exist in forms or conditions fundamentally different from life as we understand it. As our understanding of life and technology evolves, the search for extraterrestrial intelligence may reveal new dimensions to the Fermi paradox, fostering ongoing exploration into the mysteries of our universe. Life evolving on planets orbiting red dwarf stars could take on unique characteristics due to the specific environmental conditions associated with these stars. Red dwarfs are the most common type of star in the universe, making up about 75% of all stars. They are cooler and dimmer than larger stars like our Sun, leading to a habitable zone much closer to the star. This proximity presents several intriguing possibilities for the evolution of life. One significant aspect to consider is the effect of stellar activity. Red dwarfs are known for their strong stellar flares and magnetic activity, which can inundate nearby planets with radiation. If a planet were to be close to a red dwarf within its habitable zone, its atmosphere could be eroded, making it challenging for life to thrive. However, life could adapt to such conditions, potentially developing protective mechanisms against harmful radiation. For instance, organisms might evolve thicker protective layers or even biochemical pathways that can mitigate the effects of radiation. Additionally, the tidal locking phenomenon is common in planets orbiting red dwarfs. This means a planet may rotate on its axis in such a way that one side always faces the star while the other remains in perpetual darkness. The exposed side could become extremely hot, while the dark side may plunge into frigid temperatures. Life, if it were to emerge on such planets, might adapt to survive in these extreme gradients. This could lead to the development of unique biomes at the twilight zone, where temperatures are more temperate and gradients of light and heat could foster a diverse range of life forms. Furthermore, the potential for liquid water to exist on these planets substantially increases the chances for life. Even if a planet is tidally locked, water could remain in liquid form at the edges between the light and dark sides, creating a suitable environment for life to develop. This scenario might allow for the evolution of organisms that are highly specialized for their niches, leading to a diverse ecosystem adapted to varying conditions. While the environment around red dwarf stars presents unique challenges, the potential for life is still feasible. Evolution could lead to organisms with specific adaptations to radiation, temperature extremes, and niche availability. The study of such possibilities broadens our understanding of life's resilience and adaptability, expanding the horizons of where and how life might exist beyond our solar system. Biosignatures are indicators or evidence of past or present life, particularly in the context of exoplanets. These signatures can take several forms, including specific molecules, atmospheric patterns, or even surface features that suggest biological activity. The search for biosignatures is a fundamental aspect of astrobiology, as it helps scientists identify planets that may harbor life or have supported life in their history. One of the key methods for detecting biosignatures is through spectroscopy, which involves analyzing the light spectra emitted or absorbed by a planet's atmosphere. When starlight passes through a planet's atmosphere, certain wavelengths of light will be absorbed by specific molecules present in that atmosphere, creating a unique spectral fingerprint. By examining these fingerprints, researchers can detect gases that are often associated with biological processes, such as oxygen, methane, nitrous oxide, and ozone. The simultaneous presence of these gases, particularly when generated by biological sources, can serve as strong evidence of life. Advanced telescopes, both ground-based and space-based, are equipped with highly sensitive spectrometers that can conduct these analyses. Future missions, such as the James Webb Space Telescope, are designed with the capability to analyze the atmospheres of exoplanets, particularly those that lie within their stars' habitable zones. These observations can provide crucial data on temperature, pressure, and chemical composition, allowing for the identification of potential biosignatures. Another approach involves analyzing surface features, such as signs of vegetation or organic materials. For instance, the presence of chlorophyll-like molecules could suggest photosynthetic life similar to what we have on Earth. Additionally, variations in surface colors or textures could point toward biological processes that differentiate them from purely geological phenomena. Despite the promising methods for detecting biosignatures, the interpretation of this data can be complex. The observed signatures may also be produced by abiotic processes, complicating the conclusions drawn from spectroscopy or surface analysis. Therefore, researchers must approach the evidence cautiously, often requiring multiple lines of evidence to support the idea of life on an exoplanet. As technology advances and our understanding of biosignatures improves, the search for life beyond Earth will likely become more nuanced, opening new avenues for exploration and discovery in the cosmos. The formation of exoplanets typically begins within a protoplanetary disk, a rotating disk of gas and dust surrounding a young star. This process starts when material in the disk begins to coalesce due to gravitational forces, forming solid particles that collide and stick together. Over time, these particles cluster into larger bodies, eventually forming planetesimals, which can be several kilometers in size. As these planetesimals collide and merge, they gradually build up into protoplanets. Once a protoplanet reaches a certain size, its gravitational pull becomes strong enough to attract more material from the surrounding disk. This phase can lead to the formation of gas giants, where the protoplanet collects substantial amounts of gas, primarily hydrogen and helium, from the disk. In contrast, Terrestrial planets like Earth may form primarily from rocky material, with residual gases remaining in their thinner atmospheres. Migration is a critical aspect of exoplanetary evolution, with many planets moving away from their original formation locations. This is influenced by interactions within the protoplanetary disk. When a planet forms, it creates gravitational perturbations in the disk, affecting the distribution of gas and dust around it. These disturbances can lead to a transfer of angular momentum, causing the planet to migrate inward toward the star or outward to the colder regions of the disk. One common migration mechanism is known as Type 1 migration, which occurs primarily for smaller planets like Earth-sized ones as they interact with the gas in the disk. Larger planets can experience Type 2 migration, where they clear a path through the disk, experiencing more substantial movement toward the star. Another factor is the disk's density. If the disk becomes less dense over time, the gravitational interactions that facilitate migration can change, leading to the stability of some planets while causing others to shift significantly in position. These migration processes can lead to unique configurations within exoplanetary systems. For instance, the existence of hot Jupiters, gas giants found very close to their stars, suggests that they likely migrated inward after forming in cooler regions of their protoplanetary disks. Understanding how exoplanets form and migrate enriches our knowledge of their characteristics and orbits, helping researchers piece together the various histories that shape the diverse array of planetary systems we observe today. Proposed methods for interstellar communication with potential alien civilizations encompass a variety of innovative approaches, reflecting both our technological capabilities and our understanding of how intelligent life might transmit information across the vast distances of space. One of the most straightforward methods is the use of radio waves. This concept has been actively pursued through projects like the Search for Extraterrestrial Intelligence, or SETI. By transmitting and listening for radio signals in specific frequency bands, especially those that are typically associated with intelligent communications, humanity seeks signs of extraterrestrial activity. Another method involves transmitting laser beams, which can be highly directed and potentially travel vast distances with minimal dispersion. Using powerful laser pulses, scientists proposed that these signals could be sent toward nearby star systems. Laser communication could be perceived as a more efficient method than radio waves due to the narrower focus and reduced noise interference in space. If a civilization were to detect such signals, the potential for two-way communication could be greatly enhanced. The concept of sending physical probes or spacecraft to neighboring star systems has also gained attention. While limited by current technology, the idea involves using advanced propulsion systems to send small, unmanned spacecraft equipped with communication instruments. These probes could transmit data back to Earth and potentially even carry messages intended for any intelligent civilizations they might encounter. Initiatives like the Breakthrough Starshot aim to develop technology for sending tiny, lightweight probes to nearby stars at a fraction of the speed of light, thereby enabling direct exploration and communication. Lastly, there exists the possibility of encoding messages into astronomical phenomena, such as using signals generated by pulsars. These rotating neutron stars emit regular radio pulses that can be used as precise timekeeping devices. If a civilization were aware of these cosmic clocks, they might transmit messages by varying the timing or modulation of pulses in a recognizable pattern, allowing for potential interstellar communication through naturally occurring celestial signals. Despite the excitement surrounding these concepts, one major challenge persists: the vast distances between stars and the time it takes for signals to travel through space. Even at the speed of light, a signal from our closest neighboring star, Proxima Centauri, would take over 4 years to arrive. As humanity continues to explore and develop new technologies, the prospect of successfully communicating with extraterrestrial civilizations remains a tantalizing frontier in the search for life beyond Earth. Extreme planetary conditions can profoundly influence the evolution of alien life forms, leading to adaptations that may be fundamentally different from those seen on Earth. These conditions might include extreme temperatures, high radiation levels, high atmospheric pressures, or varying chemical compositions, all of which could pose unique challenges and opportunities for life. As organisms adapt to such environments, they may develop specialized features and metabolic processes that enable their survival. For instance, on a planet with extreme temperatures, whether hot or cold, life forms might evolve mechanisms to withstand or even thrive in their surroundings. On a planet with scorching surface temperatures, organisms could develop heat-resistant proteins and cellular membranes that maintain their integrity in extreme heat. Conversely, species on a frigid planet might evolve antifreeze-like compounds, preventing their bodily fluids from solidifying, much like certain extremophiles found in Earth's polar regions and deep-sea environments. Radiation levels can also shape evolutionary paths. On planets close to their stars where radiation is intense, life may have to adapt by developing protective structures or biochemical pathways to repair damage to DNA and cellular components. These adaptations could lead to organisms with robust cellular defenses, enabling them to survive harsh environments. Such adaptations might manifest as physical armor, specialized pigments to absorb harmful radiation, or complex detoxifying mechanisms. High-pressure environments, typical of gas giants or deep ocean worlds, pose another set of challenges. Life in these realms may evolve differently, perhaps adopting unique body plans suited to withstand immense pressures. For example, organisms might develop flexible bodies that can cope with the crushing weight of their atmosphere or ocean. Additionally, the availability of unique energy sources, such as highly energetic chemical reactions in the deep oceans or near hydrothermal vents, could give rise to novel metabolic pathways not seen on Earth. Lastly, the chemical environment of a planet can give rise to life forms with new biochemistries. On planets with abundant ammonia or methane, researchers speculate that life could evolve to utilize these substances instead of water, leading to entirely different biochemical processes. As scientists continue to explore the potential for life in extreme environments, whether within our solar system or on exoplanets, they uncover the vast possibilities for evolution. These diverse adaptations to extreme conditions challenge our understanding of life's limits and enhance our appreciation for the resilience and creativity of life in the universe. The existence of Planet 9 is supported by indirect evidence gathered from the unusual orbits of certain distant objects in our solar system. These objects, known as trans-Neptunian objects, are located beyond the orbit of Neptune and exhibit striking patterns in their trajectories. Many of these bodies have highly elliptical orbits that are tilted relative to the plane of the solar system, suggesting that they are influenced by the gravitational pull of a large, unseen planet. One of the key pieces of evidence comes from the clustering of these distant objects. Studies have shown that several of them have orbits that appear to align in a way that cannot be easily explained by the gravitational influence of known planets. The hypothesis is that an unknown massive planet could be exerting a gravitational force that is causing these bodies to gravitate towards a certain region of space, creating the distinct clustering patterns observed. Simulations conducted by astronomers indicate that a planet about 5 to 10 times the mass of Earth, located far beyond Pluto, could explain these observed orbital anomalies. Additionally, the estimated size and distance of Planet 9 suggest that it might be located in the outer reaches of our solar system, possibly in a highly elongated orbit that takes it several hundreds to thousands of astronomical units from the Sun. This distance would make it difficult to detect with current observational technology, as it would reflect very little sunlight. However, its presence could provide a unifying explanation for the behaviors of these distant trans-Neptunian objects. While no direct visual evidence of Planet 9 has yet been observed, researchers are actively engaged in ongoing searches with powerful telescopes, scanning the skies for signs of this elusive planet. Various sky surveys aim to gather additional data that could confirm or refute its existence. Until then, the evidence from the peculiar orbits of distant solar system bodies remains the leading reason for the scientific community's interest in Planet 9, highlighting the continuing quest to understand our solar system's structure and dynamics. The prevailing theory for the Moon's formation is the giant impact hypothesis, which suggests that the Moon was formed as a result of a colossal collision between the early Earth and a Mars-sized body often referred to as Theia. This catastrophic event, which is believed to have occurred around 4.5 billion years ago, would have caused a significant amount of debris to be ejected into space. This debris, composed of material from both Earth and Theia, subsequently coalesced under the influence of gravity to form the Moon. The impact not only created the Moon but also had profound consequences for the evolution of Earth. Initially, the collision would have caused Earth to rotate more rapidly, and the aftermath of the impact likely produced considerable heat, leading to a molten surface. As the planet cooled, the Moon began to stabilize in its orbit, gradually moving farther away from Earth over millions of years. This gravitational interaction between the Earth and the Moon played a critical role in shaping conditions on our planet. One of the significant impacts of the Moon on Earth's evolution is its effect on tides. The gravitational pull of the Moon influences the movement of ocean waters, creating tidal patterns that contribute to coastal ecosystems. These tidal forces have likely facilitated the mixing of nutrients in the oceans, promoting biological diversity and influencing evolutionary processes over geological time. Additionally, the Moon helps to stabilize Earth's axial tilt, which moderates climate variations and seasons. This stability has allowed for a more hospitable environment for life to thrive. Further, the Moon's formation and subsequent influence on Earth have contributed to the geological history of our planet. The impacts associated with the early formation of the Moon resulted in a heavily cratered lunar surface that serves as a record of the violent history of the early solar system. The study of these features provides insights into both the Moon's history and the evolution of Earth itself. Overall, the Moon's formation was not just a singular event, it has been integral in shaping the conditions that have allowed life to flourish on Earth, making it a vital component of our planet's evolutionary story. The hexagonal storm at Saturn's North Pole is a striking atmospheric phenomenon characterized by its unique six-sided shape. This hexagon, which is about 20,000 miles across, is formed by a complex interplay of fluid dynamics and atmospheric conditions unique to Saturn. While the exact mechanisms responsible for this intriguing structure are still being studied, scientists believe that it arises from the planet's rapid rotation and the interplay of various atmospheric flows. One of the primary factors contributing to the formation of the hexagon is Saturn's rotation. The planet spins on its axis approximately every 10.5 hours, which leads to the generation of powerful winds in its atmosphere. These winds, which can reach speeds of over 180 miles per hour, create persistent jet streams that flow in the same direction as the planet's rotation. Within this context, variations in wind speed and temperature can give rise to vortex formations and wave patterns. The hexagonal shape itself is thought to be the result of a standing wave pattern in the atmosphere. When the jet stream that runs around Saturn's North Pole interacts with cooler air, it can create regions of low and high pressure that stabilize into a hexagonal pattern. This phenomenon can be likened to the formation of similar shapes in fluid dynamics observed in other contexts, such as rotating fluids in laboratory experiments. Nonetheless, the specific conditions leading to the creation and maintenance of this hexagonal shape are still being investigated by scientists. Interestingly, the hexagon is not static. It has shown some variability over time. Observations have suggested that its temperature and color change with the seasons on Saturn, a reflection of the planet's axial tilt and orbit around the Sun. The ongoing study of this hexagonal storm not only enhances our understanding of Saturn's atmospheric dynamics, but also provides valuable insights into the behaviors of other planetary atmospheres, both within our solar system and beyond. The Kuiper Belt and Oort cloud are two distinct regions of our solar system that contain a wide variety of icy bodies and remnants from the early solar system. Their formation processes are tied to the history of the solar system's development and the interactions within the protoplanetary disk that surrounded the young sun. The Kuiper Belt is located just beyond the orbit of Neptune, roughly extending from about 30 to 50 astronomical units from the Sun. It is believed to have formed from the leftover material in the protoplanetary disk after the formation of the planets. As the solar system's gas and dust began to coalesce into larger bodies, many small planetesimals remained in this region. Additionally, the gravitational influence of Neptune played a significant role in shaping the Kuiper Belt. As Neptune migrated outward during its formation, it interacted with these icy bodies, scattering some into orbits and clearing out others. This dynamic interaction created a diverse population of objects that we now recognize as Kuiper Belt objects, or KBOs. The Oort cloud, on the other hand, is a more distant and spherical shell of icy bodies believed to extend from about 200 to 1,000 astronomical units from the Sun, possibly even farther. The formation of the Oort cloud is thought to be related to the later stages of planet formation and the gravitational influences exerted by the gas giants, particularly during their early orbits. As these large planets formed, their gravitational forces scattered smaller icy bodies into the far reaches of the solar system. Some of these bodies were propelled outwards beyond the Kuiper Belt and into what would become the Oort cloud. The Oort cloud is thought to be a remnant of the early solar system, containing materials that never coalesced into larger planets. Due to its distance from the Sun, the bodies in the Oort cloud remain relatively unchanged and are thought to be a source of long-period comets. When some of these cometary nuclei are perturbed, possibly by passing stars or the gravitational influence of the Milky Way, they can be nudged inward toward the inner solar system, leading to spectacular cometary appearances. Together, the Kuiper Belt and Oort cloud represent vital components of our solar system's architecture. They store clues about the conditions that prevailed in the early solar system and provide a window into the processes that influenced planetary formation and development over billions of years. Water's origin on Earth and other terrestrial planets is a fascinating subject rooted in both cosmic events and planetary processes. Scientists believe that water first appeared on our planet through a combination of materials brought by comets and asteroids. These icy bodies, remnants from the early solar system, bombarded Earth during a period known as the Late Heavy Bombardment, which occurred around 4 billion years ago. As these celestial objects collided with Earth, their ice melted, contributing to the accumulation of water on the surface. Another significant source of Earth's water may be volcanic activity. As the planet formed, water trapped within minerals in the Earth's mantle could have been released through volcanic eruptions. This process not only supplied water vapor to the atmosphere, but also played a role in creating the oceans we see today. The balance of these contributions from both ice-bearing bodies and volcanic outgassing set the stage for a watery world capable of supporting life. When we look at our neighboring terrestrial planets, the story diverges. Mercury, for instance, is too close to the Sun for any significant amount of water to remain in its atmosphere or surface. Venus, with its thick, toxic atmosphere, likely had water early on but experienced a runaway greenhouse effect that led to the loss of its oceans. Mars, however, shows tantalizing evidence of having once harbored abundant water. Signs of ancient riverbeds and polar ice caps suggest that liquid water flowed across its surface billions of years ago, though today the Martian environment is vastly different, with only trace amounts of water in the atmosphere and polar regions. Understanding the origins of water in our solar system not only sheds light on the history of Earth, but also influences the search for life beyond our planet. Identifying places like Europa, one of Jupiter's moons, which is believed to have a subsurface ocean, offers exciting possibilities for finding extraterrestrial life and further understanding the role water plays in shaping planetary environments. The peculiar tilted orbit of Uranus is one of the most intriguing features of our solar system. While the orbits of most planets in our solar system lie relatively flat and aligned, Uranus presents a unique case with an axial tilt of approximately 98 degrees. This extreme tilt means that Uranus essentially rolls around the Sun on its side. The origins of this unusual orientation are believed to stem from a combination of large impacts and gravitational interactions during the planet's formative years. Scientists propose that early in the history of the solar system, Uranus was subjected to one or more massive collisions with other celestial bodies. These collisions, involving objects roughly the size of Earth, could have imparted significant angular momentum, nudging the planet into its current tilted position. The energy generated from such a collision might have been enough to change Uranus's spin axis dramatically, creating the unique rotation and orbit we observe now. Additionally, the gravitational effects from neighboring planets, particularly those in the outer solar system, could also contribute to Uranus's unusual tilt. Over millions of years, gravitational interactions with other massive bodies like Neptune may have further influenced the stability and orientation of Uranus's orbit. This complex ballet of celestial mechanics highlights how dynamic and interconnected our solar system is. The tilted orbit of Uranus not only challenges our understanding of planetary formation, but also provides valuable insights into the processes that shape the solar system. By studying such anomalies, astronomers can gain a deeper appreciation of the diverse evolutionary trajectories that planets can experience, making Uranus a fascinating object of study. The Great Red Spot on Jupiter is a colossal storm that has fascinated scientists and astronomers for centuries. This massive anticyclone, which is larger than the Earth itself, has swirling winds that reach speeds of about 400 miles per hour. The phenomenon arises from the planet's complex atmospheric dynamics, driven by its rapid rotation and the heat generated from its interior. One of the primary causes of the Great Red Spot is Jupiter's unique atmospheric structure. The planet is composed mainly of hydrogen and helium, and as these gases interact with varying temperatures and concentrations, powerful jet streams form. These jet streams can create enormous storm systems like the Great Red Spot, where warm, rising air interacts with cooler air above, resulting in a rotating area of low pressure. This setup allows the storm to persist for an extended period, continually fueled by the planet's energy and atmospheric circulation. As for its longevity, the Great Red Spot is believed to have existed for at least 350 years, with some indications that it could be even older. Observations dating back to the late 17th century, including reports by astronomer Giovanni Cassini, provide evidence that this storm has been a permanent feature of Jupiter's atmosphere for centuries. Fortunately, recent studies suggest that while the storm has changed in size and intensity over the years, it has not diminished significantly in its existence, which raises important questions about the stability of such atmospheric phenomena. Research regarding the Great Red Spot continues to evolve, particularly with the advent of advanced space telescopes and missions like NASA's Juno spacecraft, which has been providing unprecedented insights into Jupiter's atmosphere. These studies not only deepen our understanding of Jupiter itself, but also lead to broader implications regarding atmospheric science across different planetary systems. The asteroid belt, situated between Mars and Jupiter, is a fascinating remnant from the early solar system. Its formation can be traced back to the time when planets were coalescing in a protoplanetary disk about 4.6 billion years ago. Initially, there was enough material in this disk to potentially form a planet in the region where the asteroid belt exists. However, the formation of a substantial body in this area was interrupted by the gravitational influence of nearby Jupiter. As Jupiter formed, its massive gravitational pull disrupted the accretion process. Instead of allowing the small bodies in the asteroid belt region to merge and build up into a larger planet, Jupiter's gravity caused many of these objects to be flung away, while others were left in a state of perpetual motion within the belt. This gravitational interference led to collisions among the remaining materials, which fragmented them into the smaller rocky bodies we observe as asteroids today. The asteroid belt is not a uniform collection of debris, but contains a diverse array of objects, ranging from tiny rocks to larger bodies like Ceres, which is classified as a dwarf planet. The belt itself is estimated to contain millions of asteroids, with the largest ones being several hundred kilometers across. However, even with so many objects, the vast expanse of space means that the asteroids are separated by significant distances, making the belt relatively empty. Consequently, the asteroid belt serves as a sort of time capsule, preserving the remnants of the early solar system. By studying its composition and the characteristics of the asteroids, scientists can gain insights into the building blocks of planet formation and the conditions that existed in the primordial solar system. This exploration not only enhances our understanding of our own cosmic history, but also informs the search for resources that could be invaluable for future space exploration. The possibility of subsurface oceans on icy moons such as Europa and Enceladus has captivated scientists, particularly in the search for extraterrestrial life. Both of these moons exhibit compelling evidence of liquid water existing beneath their icy crusts, and observations from various space missions have bolstered this idea. In the case of Europa, spacecraft like the Galileo orbiter provided key insights into its surface and magnetic field. The surface of Europa is marked with cracks and ridges, suggesting that water from beneath the icy crust erupts through the ice and creates new surface features. Additionally, measurements of Europa's magnetic field indicated that there is a conductive layer beneath the surface. This layer is thought to be salt water, which could be a subsurface ocean in contact with the rocky mantle, creating the right conditions for chemical reactions that might support life. Enceladus, a moon of Saturn, has also yielded remarkable evidence of subsurface oceans. Observations from the Cassini spacecraft discovered geysers erupting from the moon's south pole, shooting plumes of water vapor and ice particles into space. These eruptions suggest that there is indeed a liquid water reservoir beneath the icy shell. The composition of the plumes, which include organic molecules and simple hydrocarbons, suggests a complex subsurface environment. The detection of these materials raises intriguing questions about the moon's potential to harbor life. Both moons exhibit heat signatures aligned with gravitational models that indicate internal warmth, likely generated by tidal heating as they interact with their parent planets. The combination of these findings presents a strong case for the existence of subsurface oceans, creating a tantalizing possibility that both Europa and Enceladus could host environments suitable for life. Further exploration, including future missions planned to study these icy worlds, aims to unlock more secrets about their hidden oceans and the potential for life beyond Earth. Mercury experiences some of the most extreme temperature variations in the solar system, with temperatures soaring during the day and plunging at night. The primary reason for these dramatic fluctuations lies in its proximity to the Sun, combined with its slow rotation and lack of a significant atmosphere. During the day, temperatures can reach around 800 degrees Fahrenheit, while at night they can drop to nearly -300 degrees Fahrenheit. One of the key factors contributing to this temperature disparity is Mercury's very thin atmosphere. Lacking a substantial atmosphere means that there is little capacity to retain heat once the sun sets. Unlike Earth, where the atmosphere helps moderate temperatures by trapping heat, Mercury's tenuous atmosphere dissipates heat quickly into space. As a result, after the sun sets, temperatures can plummet rapidly due to the absence of that insulating layer. Mercury also has an unusually long day-night cycle. One rotation on its axis takes about 58 Earth days, while it takes approximately 88 Earth days to complete an orbit around the Sun. This means that the Sun shines on one side of Mercury for an extended period, allowing surface temperatures to soar before the long night brings a sharp drop in temperature. This prolonged exposure to sunlight followed by extreme darkness exacerbates the temperature swings. These extreme variations pose challenges for any potential missions to Mercury, as equipment must withstand not only intense heat, but also the freezing cold of night. Understanding the temperature dynamics on Mercury provides insights into the planet's surface processes and its geological history. Scientists are keenly interested in exploring these extremes as they offer critical information about how different celestial bodies respond to their environments in the relentless embrace of the Sun. Gravity bends light due to a phenomenon known as gravitational lensing, which occurs as a result of Einstein's theory of general relativity. According to this theory, massive objects like stars or galaxies create a curvature in the fabric of space-time around them. When light from a distant object passes near a massive body, the path of the light is altered as it travels through this curved space-time. Rather than traveling in a straight line, the light bends around the massive object, much like a marble rolling along a curved surface. This bending of light can lead to some remarkable visual effects. In some cases, it can create multiple images of the same distant object or even a complete ring-like structure known as an Einstein ring. These effects are not merely curiosities, they provide astronomers with powerful tools to study the universe. By analyzing the light bending around massive objects, scientists can infer properties about the foreground galaxies and the distribution of dark matter, an elusive component that makes up much of the universe's mass. Gravitational lensing also allows astronomers to observe very distant objects that would otherwise be too faint or small to see. By using a massive galaxy or cluster as a lens, light from galaxies located far behind it can be amplified and distorted, making them visible to telescopes. This capability has opened up new avenues for studying the early universe and understanding the formation of galaxies. The implications of this phenomenon extend beyond mere observations. Gravitational lensing provides insights into the nature of dark matter, the expansion of the universe, and the distribution of cosmic structures. It demonstrates how the universe is interconnected, with massive entities influencing the path of light across vast distances, ultimately shaping our understanding of the cosmos. Time dilation is a fascinating aspect of Einstein's theory of relativity, encompassing how the passage of time can vary depending on relative speed and gravitational fields. According to the theory, time moves more slowly for objects in motion compared to stationary observers, and it also runs slower in stronger gravitational fields. This means that for astronauts traveling at high speeds in space or experiencing significant gravitational forces, time can pass differently than for people on Earth. When it comes to space travel, the effects of time dilation have important implications. For example, if a spacecraft were to travel at a substantial fraction of the speed of light, astronauts aboard would experience time passing more slowly relative to people on Earth. This means that while only a few years may pass for the astronauts on their journey, many more years could elapse back home. This scenario has been popularly illustrated through thought experiments, such as twins where one twin travels through space at near light speed and returns home significantly younger than the twin who remained on Earth. Gravitational time dilation plays a role as well. For instance, if astronauts were to conduct missions near massive celestial bodies, such as black holes or neutron stars, the intense gravitational fields would cause their onboard clocks to tick more slowly than those on Earth. While the effects are negligible for most spacecraft in low Earth orbit, they become increasingly significant at higher speeds or with stronger gravitational influences. Understanding time dilation is crucial for missions that involve long-duration space travel, especially as humans plan potential journeys to Mars or beyond. As astronauts venture further into space, the relativistic effects of time must be considered not only for mission planning and communication, but also for the psychological implications of experiencing different time flows. Ultimately, time dilation illustrates just how interconnected time and space are, leading to profound insights about the universe and our place within it. Gravitational waves are ripples in the fabric of space-time, caused by some of the most energetic and catastrophic events in the universe. They were predicted by Albert Einstein in his general theory of relativity, which describes gravity not just as a force, but as a curvature of spacetime created by massive objects. When two massive celestial bodies, such as black holes or neutron stars, orbit each other and eventually collide, they generate gravitational waves that propagate outward at the speed of light. As these waves travel through spacetime, they produce distortions, stretching and compressing the space that they pass through. This effect can be visualized as a ripple moving across a pond when a stone is thrown in. The water surface oscillates, creating waves that affect the surrounding area. Similarly, gravitational waves stretch distances in one direction while compressing them in another. These distortions occur very subtly and are incredibly difficult to detect, which is why the discovery of gravitational waves was a monumental achievement in modern physics. The implications of detecting gravitational waves are profound for our understanding of the universe. When a gravitational wave passes through Earth, it can cause minute changes in the distance between objects, which can be measured by highly sensitive instruments like LIGO and Virgo. These observatories have successfully captured signals from events like black hole mergers, allowing scientists to gain insights into the nature of these extraordinary events, far beyond what can be achieved with conventional telescopes. Gravitational waves open up a new window into observing the universe. They provide unique information about the properties of the sources they originate from, including their mass, spin, and orbital dynamics. This capability enhances our understanding of phenomena such as supernovae, the collision of neutron stars, and even the formation and evolution of galaxies. The study of gravitational waves ultimately reshapes our view of the cosmos, revealing a deeper layer of physical reality governed by the dynamics of spacetime itself. Frame dragging is an intriguing concept in Einstein's theory of general relativity that describes how a rotating massive object can influence the spacetime around it. When an object, such as a rotating planet or star, spins, it not only curves spacetime due to its mass but also drags that spacetime along with it. This effect can be understood as a sort of twisting or pulling of the fabric of spacetime in the direction of the object's rotation. To visualize frame dragging, consider a figure skater executing a spin. As the skater rotates, the air around them gets pulled along with their motion. Similarly, a significant rotating mass like the Earth affects the spacetime around it, giving rise to this phenomenon. As it spins, the rotation creates a frame that drags the surrounding spacetime, influencing the motion of nearby objects and even light. One of the most notable demonstrations of frame dragging is the LEGEO satellites, which showed that their orbits were affected by the Earth's rotation. The satellites experienced minute changes in their orbits due to the frame dragging effect, a phenomenon predicted by general relativity. The Einstein Gravity Probe B mission further provided evidence for frame dragging by measuring the tiny shifts in the direction of a gyroscope mounted in orbit around Earth. Understanding frame dragging has profound implications in astrophysics and cosmology. It helps explain the behavior of objects in extreme environments, like those near rotating black holes. These black holes exhibit extreme frame dragging effects, resulting in what is known as the ergosphere, a region where spacetime is dragged around so rapidly that it affects the motion of anything nearby. As researchers continue to explore these effects, they deepen our understanding of gravity, motion, and the underlying structure of the universe. The expansion of the universe fundamentally alters our understanding of space-time, reshaping the way we perceive distances and the relationships between celestial objects. According to the Big Bang theory, the universe has been expanding since its inception approximately 13.8 billion years ago. This expansion occurs as space itself stretches, carrying galaxies away from each other. As a result, the distances between galaxies increase over time, leading to the observable phenomenon of redshift, where light from distant galaxies shifts toward the red end of the spectrum as they move away from us. This expansion affects the nature of spacetime by introducing the concept of a dynamic rather than static universe. In general relativity, space and time are interconnected in a four-dimensional fabric of spacetime, and the expansion modifies this fabric. The scale of space itself changes, meaning that the distances we measure are not fixed, but are influenced by the universe's growth. As galaxies recede from each other, their light takes longer to reach us, creating an observable horizon where we can only see a portion of the universe at any given moment. Moreover, this expansion has implications for the fate of the universe. There are multiple scenarios based on the rate of expansion. If the expansion continues to accelerate, as suggested by observations of dark energy, the universe could reach a state known as the Big Freeze, where galaxies become increasingly isolated over time. Alternatively, if the expansion were to slow down or reverse, it might lead to a big crunch, where the universe collapses back on itself. Each of these outcomes directly affects the geometry and structure of space-time. Ultimately, the expansion of the universe highlights the dynamic nature of space-time and emphasizes how our cosmic context informs how we perceive reality. It challenges traditional notions of distance and motion, underscoring that space itself can stretch and evolve, reflecting the ever-changing nature of the universe. Understanding these concepts helps us decode the laws governing the cosmos and deepens our grasp of the fundamental mechanics underlying existence. Wormholes are theoretical passages through space-time that create shortcuts between distant points in the universe. The concept arises from the equations of general relativity, which allow for solutions that describe a tunnel-like structure connecting two separate regions of space and time. Imagine 2 points in a flat piece of paper. While it takes time to travel across the surface, if you could fold the paper and create a direct hole between the 2 points, you would significantly reduce the distance traveled. A wormhole operates similarly, potentially allowing for quicker travel between otherwise far-off locations in space. The fascinating aspect of wormholes is that they may permit faster-than-light travel. If a spacecraft could navigate through a wormhole, it wouldn't truly be moving faster than light in the conventional sense, since it would be traversing a shortcut in space-time rather than moving through space itself. This might allow for travel across vast cosmic distances in a relatively short time, opening up incredible possibilities for interstellar exploration. However, the theoretical existence of wormholes is fraught with challenges. For one, the stability of a wormhole is a significant concern. Most solutions to the equations suggest that wormholes would be unstable, collapsing before anything could traverse them. To keep a wormhole open, exotic matter with negative energy density would be required, a form of matter that has yet to be discovered or understood in contemporary physics. Without this exotic matter, wormholes remain purely speculative. Despite their theoretical nature, wormholes raise intriguing questions about the structure of space-time and the limits of our understanding of the universe. While they provide a tantalizing glimpse into potential shortcuts for interstellar travel, practical application remains in the realm of science fiction for now. Continuing research into the properties of space-time may yield new insights into whether wormholes could indeed serve as pathways to the stars in the future. Time passes differently in strong gravitational fields due to a phenomenon known as gravitational time dilation, a concept derived from Einstein's theory of general relativity. According to this theory, gravity is not merely a force that acts at a distance, but rather a curvature of space-time caused by massive objects like stars, planets, and black holes. The stronger the gravitational field, the more pronounced the warping of space-time. When an observer is located near a massive object, time will pass more slowly for them compared to an observer situated far away where the gravitational influence is weaker. This means that if 2 clocks are synchronized and one is placed in a strong gravitational field, such as on the surface of a planet or near a black hole, while the other remains in a region with weaker gravity, the clock in the stronger field will tick at a slower rate. In practical terms, if a person were to spend time near a black hole and then return to a more distant location, they would find that more time has elapsed for those who remained further away. An interesting illustration of gravitational time dilation can be seen in the case of Earth and its satellites. For instance, the global positioning system relies on precise timekeeping to accurately determine locations. The satellites orbiting Earth, which are further from the planet's gravitational influence, experience less gravitational time dilation than clocks on the surface. As a result, engineers must account for the pronounced difference in time experienced by these satellites compared to ground-based clocks to ensure the system works correctly. This concept not only deepens our understanding of how gravity can influence the flow of time, but also has significant implications in astrophysics and cosmology. It enhances our comprehension of how various phenomena, such as black holes and neutron stars, might behave in extreme environments. Overall, gravitational time dilation remains a tantalizing reminder of the intricate relationship between gravity, space-time, and the nature of time itself. The twin paradox is a thought experiment in the realm of special relativity that highlights the effects of time dilation when objects move at relativistic speeds. The scenario involves identical twins, one of whom embarks on a journey into space at a significant fraction of the speed of light, while the other remains on Earth. Upon the traveling twins' return, it is found that they are younger than their Earth-bound sibling. This seemingly paradoxical situation challenges our intuitive understanding of time and illustrates how relative motion influences the passage of time. At the heart of the twin paradox is the principle of time dilation, a key concept of Einstein's theory of special relativity. According to this theory, time appears to pass more slowly for objects moving at high velocities compared to stationary observers. For the twin in space, traveling at such speeds, their onboard clock ticks more slowly relative to the clock of the twin who stayed on Earth. This means that while the journey may only take a few years for the traveling twin, many more years would pass for the twin left behind. What adds to the intrigue of the twin paradox is that both twins can consider themselves to be at rest in their own frame of reference while the other is moving. However, the critical distinction lies in the fact that the traveling twin undergoes acceleration and deceleration during their journey, particularly when turning around to return to Earth. This change in velocity breaks the symmetry of the situation, allowing the traveling twin to effectively experience less time overall. The twin paradox beautifully demonstrates one of the remarkable consequences of special relativity, that time is not an absolute constant but is instead relative, dependent on the observer's frame of reference. This thought experiment has been confirmed through various experiments, including those involving atomic clocks flown on high-speed jets, showing that the principles of time dilation hold true in practice. As a result, the twin paradox serves as a compelling illustration of the non-intuitive yet profound nature of time in the context of relativistic physics. The curvature of space-time is a fundamental concept in Einstein's theory of general relativity, and it provides a profound explanation of orbital motion. Instead of viewing gravity as a force that pulls objects together, general relativity describes gravity as the result of massive objects warping the fabric of space-time around them. When a planet, star, or any massive body sits in this curved space-time, it creates a dent, causing objects nearby to move along curved paths. To understand how this works in the context of orbital motion, consider the example of the Earth orbiting the Sun. As the Sun has a significant mass, it curves the spacetime around it. The Earth moving through this curved spacetime does not simply fall straight into the Sun due to gravity. Instead, it follows a path determined by the curvature created by the Sun's mass. This path is what we perceive as the elliptical orbit of the Earth. When an object is in orbit, it is continuously falling toward the massive body it orbits. But because it also has a forward velocity, it moves sideways as it falls. This balance between the gravitational pull of the massive body and the object's forward motion results in a stable orbit. Essentially, the object is following a geodesic, the shortest path between 2 points in curved space-time, but appears as an orbital path to us. This concept not only explains the motion of planets around stars, but also extends to other celestial interactions. For instance, moons orbit planets, and even binary star systems exhibit this behavior, where each star follows an orbit around a common center of mass, influenced by the curvature of spacetime produced by their respective masses. The curvature of spacetime also aids in understanding phenomena like gravitational assists used in space travel. By calculating the geometry of spacetime around planetary bodies, spacecraft can use their motion through this curvature to gain speed and alter their trajectory toward other destinations in the solar system. This understanding has revolutionized both our theoretical framework for gravity and the practical methods we use in space exploration, illustrating the elegant interplay between mass, spacetime, and motion in the universe. The relationship between mass, energy, and the curvature of spacetime is elegantly summarized by Einstein's famous equation, E equals mach squared. This equation establishes that mass and energy are interchangeable. They are different forms of the same underlying quantity. This interchangeability plays a critical role in how mass and energy influence the curvature of spacetime, an essential aspect of Einstein's general theory of relativity. In this framework, mass and energy are not just passive attributes, but active participants in shaping the geometry of spacetime. According to general relativity, the presence of mass and energy results in the warping or curvature of spacetime around them. This curvature is what we perceive as gravity. For instance, when a massive object like the Earth is present, it causes a dent in spacetime, creating a region where the curvature is more pronounced. As a result, other objects nearby will follow paths determined by this curvature, leading to orbital motion and gravitational attraction. Furthermore, not only does mass create curvature, but energy does as well. All forms of energy, such as potential energy, kinetic energy, and thermal energy, contribute to the overall mass-energy content of a system. This means that both mass and energy can influence the curvature of space-time equally, leading to gravitational effects. For example, the energy released in nuclear reactions or the motion of particles can produce local changes in the curvature, affecting nearby objects. Additionally, the curvature of spacetime itself can change as mass and energy fluctuate over time. For instance, when a massive star undergoes a supernova explosion, the energy released and the redistribution of mass can alter the curvature of spacetime in its vicinity, with profound implications for surrounding objects and radiation. The interplay between mass, energy, and the curvature of spacetime creates a dynamic and interconnected framework that underpins our understanding of gravity. By recognizing that both mass and energy contribute to the bending of spacetime, we gain deeper insights into the fundamental workings of the universe, influencing everything from planetary motion to the behavior of light in gravitational fields. Gravitational assists, also known as gravity assists or slingshot maneuvers, are a clever technique used in space exploration to boost the speed and trajectory of spacecraft without expending additional fuel. This method takes advantage of the gravitational pull of a planet or other celestial body. When a spacecraft approaches a planet, it can use the planet's gravity to change its velocity and direction, gaining energy in the process. The mechanics of a gravitational assist work as follows. As the spacecraft approaches the planet, it falls into the gravitational well created by the planet's mass. As it moves past the planet, the spacecraft accelerates due to the gravitational pull, gaining speed. Importantly, the spacecraft also obtains a component of the planet's orbital momentum as it is flung outward. After passing by the planet, the spacecraft continues on its trajectory, now traveling faster and often on a new path that can be directed toward its intended destination. This maneuver allows the spacecraft to conserve fuel, making interplanetary missions more feasible. Gravitational assists have significant implications for deep space exploration. By carefully plotting a spacecraft's trajectory and timing its approach to a planet, mission planners can achieve remarkable distances and speeds that would otherwise require a substantial increase in fuel. For instance, the Voyager missions, which explored the outer planets in the 1970s and 1980s, utilized multiple gravitational assists from Jupiter and Saturn to gain enough velocity to reach their targets and continue on to the outer reaches of the solar system. Additionally, gravitational assists can also aid in the transfer of spacecraft toward more distant destinations, such as the outer planets or even interstellar space. They allow scientists to explore multiple celestial bodies within a single mission. For example, the Galileo spacecraft used gravitational assists to travel to Jupiter, while the New Horizons mission employed a gravity assist from Jupiter to reach Pluto swiftly. In a broader context, gravitational assists demonstrate the intricate interplay between celestial mechanics and space travel. By harnessing the natural movements and gravitational forces of planets, spacecraft can maximize their efficiency, exploring distant reaches of the solar system and beyond, while making significant advancements in our understanding of the universe. Nuclear propulsion holds considerable promise for enhancing the efficiency and capabilities of space travel. Unlike traditional chemical rockets, which rely on the combustion of propellant that generates thrust, nuclear propulsion systems use nuclear reactions to produce energy. This approach can lead to multiple potential applications, particularly for deep space missions, where efficiency and long-duration travel are critical. One of the primary applications of nuclear propulsion is interplanetary travel. Nuclear thermal propulsion operates by using a nuclear reactor to heat a propellant, such as hydrogen, which is then expelled to produce thrust. This system can provide a much higher specific impulse, an important measure of propulsion efficiency, than conventional rocket engines. As a result, missions to Mars or even the outer planets could be completed in significantly shorter timeframes, reducing the time astronauts spend in space and the associated risks of long-duration missions. Another innovative application is in the concept of nuclear electric propulsion. This system employs nuclear reactors to generate electricity, which then powers ion thrusters. While ion thrusters produce low thrust, they are highly efficient and can operate for extended periods. Such propulsion allows for gradual, continuous acceleration, making it well-suited for deep space exploration and ferrying cargo over vast distances. A spacecraft powered by nuclear electric propulsion could reach significant speeds over time, potentially enabling missions to the asteroid belt and beyond. Nuclear propulsion also opens up possibilities for crewed missions to more distant destinations, such as the moons of Jupiter and Saturn. The ability to reduce travel times can make it feasible to conduct missions that are currently unapproachable due to the limitations of chemical propulsion. This could also facilitate future missions aimed at resource utilization, such as mining asteroids or exploring the icy worlds in the outer solar system for signs of life. Additionally, the reliability of nuclear systems provides another layer of advantage. Nuclear reactors, once initiated, can produce energy continuously for long durations without the need for refueling, making them attractive for sustained operations in space. This longevity can support research outposts or habitats on distant planetary bodies. As advancements continue in nuclear technology and safety protocols, the potential applications of nuclear propulsion in space travel could revolutionize our capabilities for exploration, allowing humanity to reach farther into the solar system while optimizing efficiency and safety. Space elevators present a groundbreaking concept that could dramatically change the way we access orbit and transport materials and people into space. The fundamental idea involves a structure extending from the surface of the Earth to a point beyond geostationary orbit, where the centrifugal force balances the gravitational pull. This structure would consist of a strong tether or cable anchored to the Earth, with a counterweight positioned in space to maintain tension. The potential advantages of space elevators are immense. Currently, launching payloads into space requires vast amounts of energy and expensive rockets that operate using chemical propulsion. Space elevators could significantly reduce the cost of sending materials to orbit. Instead of relying on rockets, vehicles known as climbers could ascend along the tether, using electrical power to move up and down. This could result in lower operational costs and increased frequency of launches, making it economically feasible to transport larger quantities of cargo into space. In addition to cost efficiency, space elevators could enable a wider range of activities in orbit. With more readily accessible transport, Industries such as space tourism, satellite launching, and even planetary exploration could flourish. This heightened accessibility to space could facilitate the development of orbital infrastructures, including research stations, manufacturing facilities, and habitats, leading to an expanded human presence in space. Furthermore, a space elevator would provide a continuous or rapid connection between Earth and orbit, avoiding the long delays often associated with traditional launch schedules. Such a constant flow of supplies and personnel could be vital for maintaining operations for long-term missions, like those to the Moon or Mars. Space elevators might also support the construction of more sophisticated space systems, such as solar power satellites that could collect energy in space and beam it back to Earth. While the concept of space elevators is appealing, several challenges must be overcome before they become a reality. The materials used for the tether need to possess extraordinary strength and lightweight properties. Current materials like carbon nanotubes are being researched for this purpose. Additionally, overcoming technical hurdles related to stability, external forces like weather, and safety protocols will be crucial. Despite these challenges, the vision of space elevators represents a transformative approach to space access. If realized, they could enable a paradigm shift in our ability to explore and utilize space, making it more accessible and sustainable for future generations. Asteroid mining presents both remarkable potential benefits and significant challenges as humanity looks to the cosmos for resources. The concept of extracting minerals and materials from asteroids offers an innovative solution to supplement terrestrial resources while providing raw materials essential for space exploration and infrastructure development. One of the primary benefits of asteroid mining is the vast availability of valuable materials. Many asteroids are rich in metals like platinum, gold, and rare earth elements, which are crucial for various technologies, including electronics and renewable energy systems. Extracting these materials from asteroids could alleviate the pressures of resource scarcity on Earth, reduce the environmental impact of terrestrial mining, and potentially lead to new economic opportunities. Additionally, materials sourced from asteroids could support future space missions by providing building materials, fuels, and even water for life support systems in deep space. However, the challenges of asteroid mining are substantial. One of the foremost difficulties is the technological requirement to identify, reach, and mine asteroids. Space missions must first locate suitable asteroids, some of which may be small or orbiting in distant regions of the solar system. Developing efficient propulsion systems, robotic mining technologies, and autonomous systems for remote operation and extraction will be critical. The logistics of transporting mined materials back to Earth or using them in space also present significant engineering challenges. Another challenge involves the legal and regulatory frameworks governing space resources. Current international space treaties, such as the Outer Space Treaty of 1967, do not address the ownership of materials extracted from celestial bodies. Establishing clear guidelines and agreements will be essential to facilitate commercial ventures in asteroid mining while preventing conflicts over space resources. Moreover, there are economic considerations to weigh. The initial investment for asteroid mining ventures is likely to be substantial, and profitability may depend on overcoming technological barriers and ensuring that extracted materials can be transported and utilized in a cost-effective manner. The market for asteroid-sourced materials must also be defined, considering the potential impact on existing Earth-based commodities. Despite these challenges, the possibilities of asteroid mining are truly captivating, as they could pave the way for a new era of resource utilization beyond Earth. As technology advances and our understanding of the space environment expands, asteroid mining could not only provide essential materials for life on Earth, but also support long-term human presence in space. In doing so, it may help drive innovation, reduce terrestrial resource demands, and unlock the solar system's potential for future generations. Shielding spacecraft and astronauts from cosmic radiation is a critical consideration for long-duration space missions, such as those planned for Mars or beyond. Cosmic radiation consists of high-energy particles originating from various sources, including the Sun and distant supernovae, which can pose serious health risks to astronauts. As these particles penetrate biological tissue, they can cause damage to DNA and increase the risk of cancer and other health issues. Therefore, effective radiation protection is essential to ensure the safety and well-being of astronauts during extended periods in space. One approach to shielding involves the spacecraft structure itself. Engineers can design spacecraft using materials with high atomic numbers, such as lead or polyethylene, which can absorb or deflect radiation. In practice, this can mean incorporating walls of different materials into the spacecraft's design, creating layers that help mitigate the penetration of harmful particles. Additionally, the layout of the spacecraft can be optimized to place critical areas, such as living quarters, behind thicker shielding or within science bunkers, areas specifically designed to provide extra protection during solar particle events. Another strategy involves utilizing the massive supplies and equipment within the spacecraft as a form of passive shielding. The cargo and water supplies can serve as effective buffers against radiation. This technique not only provides a dual purpose of utilizing available resources, but also allows for a more efficient use of space within the spacecraft. For missions to Mars, careful planning can ensure that the resources needed for the journey can also contribute to radiation protection. Active shielding is another area of ongoing research, which involves creating electromagnetic fields to deflect charged particles away from the spacecraft. This technology is still in the experimental phase, but researchers are exploring the possibility of using magnetic or electrostatic fields to create a protective bubble around a spacecraft. While this concept holds great promise, significant developments in technology and engineering will be required to make it a practical solution. Finally, monitoring and timely communication about radiation levels are crucial for astronaut safety. Spacecraft can be equipped with radiation detectors to provide real-time data about cosmic radiation exposure. Establishing protocols to allow astronauts to take refuge in more shielded areas during high radiation events, such as solar flares, can further minimize their exposure. As we increase our ambitions for deep space exploration, addressing cosmic radiation will remain a priority. By combining innovative shielding techniques with effective mission planning and real-time monitoring, we can help protect astronauts as they venture farther into the cosmos, unlocking new opportunities for discovery and exploration. Recent advancements in exoplanet imaging technologies have significantly improved our ability to detect and study planets outside our solar system. As astronomers delve deeper into the exploration of these distant worlds, several cutting-edge techniques have emerged, enhancing our capability to capture images of exoplanets and analyze their atmospheres. One of the most noteworthy developments has been the use of adaptive optics combined with powerful ground-based telescopes. Adaptive optics systems help correct for the distortions caused by the Earth's atmosphere, allowing telescopes to achieve sharper images. This technology is particularly beneficial for observing exoplanets, which are often lost in the glare of their parent stars. By minimizing atmospheric interference, astronomers can identify and characterize the light from exoplanets more effectively. Notable observatories, including the Keck Observatory in Hawaii and the Very Large Telescope in Chile, have successfully employed these techniques to image exoplanets directly. Another promising innovation is the use of coronagraphs and starshades, which are designed to block the light from a star, allowing for the observation of nearby exoplanets. These instruments can selectively filter out starlight to reveal planets that would otherwise remain obscured. NASA's upcoming missions, like the James Webb Space Telescope and the Roman Space Telescope, are set to utilize advanced coronagraph technology. The James Webb Space Telescope, with its powerful infrared capabilities, aims to provide unprecedented insights into the atmospheres of exoplanets, potentially identifying the presence of molecules indicative of habitability or even life. Furthermore, innovations in spectroscopic techniques have allowed astronomers to study the chemical compositions and atmospheres of exoplanets. By analyzing the spectrum of light that passes through or reflects off an exoplanet's atmosphere, researchers can identify the presence of specific molecules such as water vapor, carbon dioxide, and methane. The increasing precision and sensitivity of spectrometers contribute significantly to our understanding of exoplanet environments. This is particularly important in the search for potentially habitable worlds, as atmosphere analysis can reveal conditions suitable for life. Lastly, machine learning and artificial intelligence are playing an increasingly vital role in processing the vast amounts of data generated by these advanced imaging technologies. These methods can identify patterns and detect exoplanets with greater speed and efficiency, allowing for more discoveries and better characterization of known exoplanets. As these technologies continue to evolve, they promise to enhance our understanding of the diverse array of planetary systems throughout the galaxy. The ongoing advancements in exoplanet imaging have sparked excitement in the field of astronomy, driving forward our efforts to explore distant worlds. As we continue to refine these technologies, the possibility of discovering Earth-like planets and understanding the conditions necessary for life becomes ever more attainable. Advanced artificial intelligence systems are poised to revolutionize space exploration and data analysis in several transformative ways. As missions become increasingly complex and the volume of data collected during space missions grows exponentially, AI offers powerful tools to enhance our understanding of the cosmos and improve operational efficiencies. One significant contribution of AI lies in data processing and analysis. Space telescopes and satellites generate massive amounts of data, particularly in fields like astronomy and planetary science. Advanced machine learning algorithms can sift through this data much more efficiently than traditional methods, identifying patterns, anomalies, and potential areas of interest. For example, AI has been employed in the search for exoplanets, where algorithms can detect subtle signals in light curves that indicate the presence of planets transiting their host stars. This capability allows scientists to discover new celestial bodies at an accelerated pace. AI systems can also enhance image analysis, which is crucial for missions involving planetary exploration and satellite imaging. Techniques like convolutional neural networks can process images from space, helping to identify geological features, track atmospheric changes, or monitor environmental shifts on planetary bodies. For instance, AI has been effectively used to analyze images of Mars, helping scientists classify surface features and identify regions of potential scientific interest for future missions. Moreover, AI-driven autonomous systems can vastly improve the operational aspects of space missions. Autonomous spacecraft equipped with AI can make real-time decisions based on environmental data, optimizing routes and resource management. This capability is particularly valuable for deep space missions, where communication with Earth may have significant delays. An intelligent system can analyze conditions and execute adjustments without waiting for instructions, increasing mission efficiency and safety. Additionally, AI can facilitate enhanced simulation and modeling of space environments. By using advanced algorithms to simulate various scenarios, scientists can better understand complex systems and predict outcomes. This modeling is critical for mission planning, risk assessment, and developing contingency strategies for unforeseen challenges during space missions. Finally, AI can foster collaboration across various scientific disciplines by integrating diverse datasets from different sources, such as geological, biological, and atmospheric studies. This interoperability allows researchers to generate more holistic understandings of celestial phenomena and informs the development of next-generation exploration strategies. Advanced AI systems are set to play a pivotal role in enhancing space exploration and data analysis. From accelerating data processing to enabling autonomous operations and sophisticated modeling, the integration of AI technologies promises to unlock new frontiers in our exploration of the universe, making future missions more efficient, informed, and impactful. The potential applications of 3D printing technology in space colonization are vast and transformative, offering innovative solutions to the unique challenges associated with establishing human habitats beyond Earth. This technology allows for the localized production of components, tools, and even entire structures directly in space, minimizing the need for transporting materials from Earth and making space missions more sustainable. One of the most significant advantages of 3D printing in space colonization is the ability to manufacture essential items on site using local resources. For example, materials found on planetary bodies, such as regolith on the Moon or Mars, can be used as feedstock for 3D printers. This process, known as in situ resource utilization, enables the construction of habitats, infrastructure, and equipment needed for long-term missions without relying heavily on supply shipments from Earth. By reducing the dependency on Earth-launched materials, mission costs and logistical complexities can be significantly decreased. 3D printing can also play a crucial role in creating repair parts and tools. Equipment malfunction is a common issue during long-duration missions, and having the capability to print replacement parts on demand can prevent delays and ensure continuous operations. Astronauts can fabricate specialized tools tailored to specific tasks, thereby enhancing efficiency and effectiveness in maintaining equipment and conducting scientific research. Beyond structural components and repairs, 3D printing technology holds promise in producing life support systems. For instance, researchers are exploring the printing of biological tissues and even food. Imagine a scenario where astronauts can print fresh food items, thereby improving nutrition and morale on long missions. In the realm of biological production, there are ongoing studies into how 3D bioprinting could be used to create tissue structures or grow microorganisms that can support life support systems or recycle waste. Another application is in the field of architecture and habitat design. With 3D printing, architects can rapidly prototype and create complex structures that are optimized for the extreme conditions of space. Innovative designs can be developed that enhance thermal insulation, radiation protection, and structural integrity, ensuring that habitats can withstand harsh environments while providing comfortable living spaces for future inhabitants. As 3D printing technology continues to evolve, its integration into space colonization efforts can ultimately lead to self-sustaining extraterrestrial habitats. This capability not only enhances the feasibility of long-term human presence in space, but also paves the way for future exploration and utilization of resources across the solar system. By empowering astronauts to fabricate what they need within their environment, 3D printing opens up new possibilities for the expansion of humanity beyond Earth. Space-based solar power systems are an innovative concept designed to harness solar energy in space and transmit it back to Earth for use. The basic principle involves placing solar power satellites in orbit, where they can capture the sun's energy without atmospheric interference or the interruptions caused by weather or the day-night cycle. These solar power satellites typically consist of large arrays of photovoltaic cells that convert sunlight into electricity. Once the solar energy is collected, it can be converted into a suitable form for transmission, often through microwave or laser beams. The energy is then aimed at a designated receiving station on Earth, where it is collected and converted back into electricity for distribution to the power grid. The potential benefits of space-based solar power systems are substantial. One of the most significant advantages is the ability to generate clean energy continuously. Unlike terrestrial solar power, which is limited to daylight hours and affected by weather conditions, space-based systems can capture solar energy around the clock. This constant energy supply could help mitigate some of the challenges associated with renewable energy, such as intermittency and storage. Additionally, space-based solar power can provide energy to remote or disaster-stricken areas that lack robust power infrastructure. With the ability to beam energy to different locations, these systems could offer a flexible solution for power distribution, supporting humanitarian efforts, military operations, and emergency response initiatives. Moreover, the deployment of space-based solar power systems has the potential to contribute to reducing greenhouse gas emissions. By generating solar energy in space, the need for fossil fuel-based power generation could be diminished, making a significant positive impact on climate change efforts. However, there are challenges to overcome before space-based solar power becomes a reality. The technological hurdles of building and launching large satellites, ensuring efficient energy conversion, and establishing reliable transmission methods are complex and costly. Additionally, safety concerns regarding the health effects of high-intensity microwave beams or lasers need thorough investigation and regulation. Despite these challenges, the concept of space-based solar power presents an exciting pathway for sustainable energy generation. Continued research and development in this area could yield breakthroughs that enable the efficient capture and distribution of solar energy from space, potentially transforming the way we power our world in the future. Long-term human habitation in space presents a myriad of challenges that must be addressed to ensure the safety, health, and well-being of astronauts on extended missions, such as those to Mars or lunar outposts. Key challenges include microgravity effects, radiation exposure, psychological well-being, resource management, and the sustainability of life support systems. One of the major challenges is the physiological impact of prolonged exposure to microgravity. Astronauts experience muscle atrophy and bone density loss due to the lack of gravitational forces, which can lead to serious health issues over time. Potential solutions include implementing regular exercise regimens using advanced exercise equipment designed for microgravity environments. Additionally, researchers are exploring nutritional interventions and pharmaceutical therapies to mitigate these effects and maintain astronaut health during long missions. Radiation exposure is another critical concern, as deep space travel subjects astronauts to higher levels of cosmic radiation and solar particle events than those experienced on Earth. Long periods of radiation exposure can increase the risk of cancer and other health problems. To address this challenge, spacecraft could be designed with additional shielding using materials that effectively absorb or deflect radiation. Moreover, employing habitats with layered walls or using natural resources, such as lunar regolith or Martian soil for shielding, may enhance protection. Psychological well-being is crucial for maintaining mission success. Long-duration missions can lead to feelings of isolation, confinement, and stress among crew members. Solutions involve fostering social support systems and ensuring effective communication with teams on Earth. Creating communal spaces within habitats and incorporating recreational activities can help to promote mental well-being. Research into team dynamics and conflict resolution also plays a vital role in preparing crews for the challenges of living and working together in confined spaces for extended periods. Resource management is essential for sustaining life in space. Reliable systems for water recycling, air purification, and food production are fundamental to long-term habitation. Closed-loop life support systems that recycle air and water can minimize waste and resource needs. Advances in hydroponics and aeroponics can facilitate the growth of fresh food in space. Research into growing crops in microgravity and developing efficient food production systems are ongoing, with potential lunar or Martian greenhouses providing not only nutrition, but also psychological benefits for astronauts. Finally, developing autonomous systems capable of repairing and maintaining habitats will be crucial. As missions progress further from Earth, timely support becomes more challenging. Robotics, artificial intelligence, and automation technologies can provide essential assistance by conducting repairs and monitoring life support systems, allowing for greater autonomy and reliability in the harsh space environment. Addressing these challenges for long-term human habitation in space requires a multifaceted approach. By investing in research and technological advancements, we can create safe, sustainable environments for astronauts on extended missions, enabling humanity to explore further into the solar system and potentially establish a permanent presence beyond Earth. If a gamma-ray burst were directed at Earth, the consequences could be catastrophic. Gamma-ray bursts are among the most powerful explosions in the universe, releasing massive amounts of energy in the form of gamma radiation over a short period, often just a few seconds to several minutes. These bursts are believed to occur during the collapse of massive stars into black holes or the merger of neutron stars. If such an event occurred in our cosmic neighborhood and was aimed directly at Earth, the intense gamma radiation could have devastating effects on our planet's atmosphere and biosphere. One of the primary concerns is the impact on the ozone layer, which protects life on Earth from harmful ultraviolet radiation. The energy from a nearby gamma-ray burst could deplete the ozone layer significantly, allowing increased levels of ultraviolet radiation to reach the surface. This increase in UV radiation could result in widespread ecological destruction, harming the phytoplankton that form the base of the marine food chain, and ultimately affecting plant life and human health. Moreover, the immediate radiation from the burst could be lethal to unprotected life forms, especially those exposed to high altitudes or in space. Spacecraft and astronauts in low Earth orbit would face extreme radiation doses, potentially rendering them incapacitated or inducing radiation sickness. The effects on surface life would depend on the distance of the burst. A nearby gamma-ray burst could cause widespread extinction events, while one further away might lead only to increased radiation exposure. Additionally, the electromagnetic pulse generated by such a powerful event could disrupt electronic systems and satellites, leading to potential blackouts and loss of communication. The cascading failure of technology could have far-reaching implications for human society, affecting everything from power grids to telecommunications. Fortunately, the probability of Earth encountering a gamma-ray burst from within a dangerous proximity is extremely low. Most known gamma-ray bursts originate from galaxies far beyond our own, typically occurring millions or even billions of light-years away. Scientists continuously monitor the cosmos for such high-energy events, understanding that while they are fascinating phenomena, the direct threat to Earth remains minimal. Nonetheless, studying gamma-ray bursts helps researchers understand fundamental processes in the universe and reinforces the importance of protecting our planet's delicate ecosystems from potential cosmic disasters. Planetary impacts have played a significant role in shaping the evolution of life on Earth and may similarly affect other celestial bodies in ways that influence their potential for life. These events, which include collisions with asteroids and comets, can have both devastating and transformative effects on planetary environments. On Earth, one of the most notable impacts occurred approximately 66 million years ago when a massive asteroid struck near the present-day Yucatan Peninsula. This event is widely believed to have caused the mass extinction, known as the Cretaceous-Paleogene extinction event, which led to the demise of approximately 75% of all species, including the non-avian dinosaurs. The immediate aftermath of such a catastrophic impact would have included massive fires, tsunamis, and a nuclear winter effect, with dust and debris blocking sunlight and disrupting photosynthesis. This dramatic alteration of environmental conditions created opportunities for other species to adapt and flourish. The extinction of dominant groups like the dinosaurs permitted mammals to diversify and eventually led to the rise of primates and ultimately humans. In addition to causing mass extinctions, planetary impacts can also serve as agents of evolutionary change by introducing new materials and chemicals into an environment. For example, certain impacts may deliver water and organic compounds to planets, potentially kickstarting the development of life. This idea aligns with the panspermia hypothesis, which suggests that life or its precursors may be distributed throughout the universe via comets and asteroids. Such deliveries could play a crucial role in creating habitable conditions on rocky planets, enhancing the prospects for life's emergence. Moreover, impacts can influence the geological and climatic dynamics of a planet. The heat generated by an impact can lead to volcanic activity, creating new landforms and altering atmosphere composition. Such changes can, in turn, create diverse ecosystems and habitats, promoting biodiversity. For example, volcanic eruptions following a large impact could lead to nutrient-rich soils, supporting new forms of life that adapt to the changing environment. On other planets, the effects of impacts may also play a significant role in the potential for life to emerge. For instance, Mars, which experienced numerous impacts throughout its history, may have once had conditions suitable for life. The delivery of water and organic materials through impacts could have contributed to its early environment. Similarly, moons like Europa or Enceladus with subsurface oceans may have been subjected to impacts that introduce necessary compounds for life. Planetary impacts are complex phenomena that can drastically shape the course of evolution by causing mass extinctions, nurturing new life, and influencing environmental conditions. Their role in the history of life on Earth and the potential for life on other planets underscores the intricate relationships between celestial events and the evolution of living organisms. Understanding these processes not only informs our knowledge of Earth's history, but also guides the search for life beyond our planet. A nearby supernova explosion could have profound consequences for Earth and its biosphere, depending on the proximity of the event. Supernovae are powerful stellar explosions that occur at the end of a massive star's life cycle. When a star exhausts its nuclear fuel, it can no longer support its own mass and may explode, releasing an immense amount of energy and ejecting heavy elements into space. If a supernova were to occur relatively close to Earth, within about 50 to 100 light years, there could be significant effects. One of the most immediate consequences would be the increase in radiation exposure. A supernova emits a substantial amount of high-energy radiation, including gamma rays and X-rays. This radiation could have harmful effects on our atmosphere, potentially depleting the ozone layer. A diminished ozone layer would expose Earth's surface to higher levels of ultraviolet radiation, which can lead to increased incidence of skin cancer, cataracts, and damage to ecosystems. Additionally, the shockwave generated by the explosion could affect the Earth, although the impact would diminish with distance. The shockwave could potentially disrupt the atmospheres of surrounding planets and even interact with the solar wind, affecting the Earth's magnetosphere. This interaction could lead to geomagnetic storms, which can disrupt power grids and communication systems, as seen during strong solar storms. Another consequence of a nearby supernova could involve the introduction of heavy elements into our solar system. Supernovae are responsible for producing many of the heavier elements found in the universe, such as gold and uranium. The explosion would scatter these elements across space and, depending on the trajectory of the debris, some of it could be incorporated into the solar system. This process contributes to the cosmic abundance of materials essential for planet formation and may have historical significance for the chemistry of Earth's early environment. However, it's important to note that despite these potential consequences, the likelihood of a supernova occurring in our cosmic neighborhood within the near future is low. The nearest candidates for a supernova, such as Betelgeuse in the Orion constellation, are still too far away to pose a significant risk. Even when they eventually do explode, the effects on Earth would depend on their distance and the energy of the explosion. Ultimately, while a nearby supernova explosion could have notable effects on Earth, including increased radiation exposure, atmospheric disruptions, and the introduction of heavy elements, the risks are largely theoretical at present. Ongoing research into stellar evolution and cosmology continues to enhance our understanding of these powerful cosmic events and their potential implications for our planet. A reversal of Earth's magnetic field, known as geomagnetic reversal, occurs when the planet's magnetic north and south poles switch places. This phenomenon has happened numerous times throughout Earth's history, with the last significant reversal, the Brunhes-Matuyama reversal, occurring approximately 800,000 years ago. While geomagnetic reversals themselves are natural events that have occurred over geological timescales, their consequences for life on Earth and our technological society can raise intriguing questions. One immediate effect of a magnetic field reversal would be a weakening of the magnetic field during the transition. Earth's magnetic field acts as a protective shield against cosmic radiation and solar wind, deflecting charged particles and preventing them from stripping away the atmosphere or causing harm to living organisms. If the magnetic field weakened, it could allow greater amounts of radiation to penetrate the atmosphere. This increase in radiation exposure might impact various forms of life, particularly those that are more vulnerable, such as animals without protective outer layers or those that dwell at lower altitudes. However, it is important to note that past geomagnetic reversals did not coincide with mass extinctions, suggesting that life on Earth is likely to adapt to changes in radiation levels over time. Many organisms, particularly those at ground level or under the ocean, have ways of shielding themselves from radiation that could mitigate some of the potential negative effects. In addition to biological effects, a magnetic field reversal could have consequences for technology and infrastructure. Modern technologies, particularly satellite systems and GPS networks, rely on the stability of Earth's magnetic field for navigation and communication. Fluctuations or anomalies in the magnetic field could lead to disruptions in these systems, impacting global positioning and data communication. Astronauts aboard the International Space Station, who are above much of the protective layer of the magnetic field, might also face increased radiation exposure, necessitating adjustments to mission protocols. Finally, the psychological and societal implications of a magnetic field reversal might be noteworthy. As the phenomenon unfolds, it could lead to public concern or misunderstanding about its effects. Clear communication from scientists and authorities regarding the nature of geomagnetic reversals, their historical context, and contemporary implications would be essential to mitigate panic and promote informed discussions. Overall, while a reversal of Earth's magnetic field has potential implications for life and technology, historical evidence suggests that Earth and its inhabitants can endure and adapt to such changes. Ongoing research into the dynamics of Earth's magnetic field, along with advancements in understanding the implications for both biological systems and technology, will continue to illuminate how this natural phenomenon influences our planet. In the distant future, our Sun is expected to enter the red giant phase as it exhausts its nuclear fuel. This stage, anticipated to occur in about 5 billion years, will have profound effects on the solar system, especially on the inner planets, including Earth. As the Sun evolves into a red giant, its outer layers will expand dramatically, increasing its size to potentially engulf the inner planets. This transformation is driven by the Sun's shift from hydrogen fusion in its core to helium fusion, which causes the outer envelope to swell and cool. As a result, the surface temperature of the Sun will drop, giving it a reddish hue, but its luminosity will increase significantly. The brightness of the Sun during this red giant phase could be several thousand times greater than its current output, resulting in a much hotter and more intense solar radiation received by the inner planets. The immediate effect on Earth will be dramatic heating. As the Sun expands, temperatures on Earth are expected to rise drastically, leading to the evaporation of oceans and the loss of the atmosphere. Any remaining life on the planet would be unable to survive in such extreme conditions. The intense heat would likely strip away the biosphere, rendering the planet uninhabitable long before it might be physically engulfed by the Sun. For the outer planets and their moons, the effects will vary. While they may not be destroyed by the Sun's expansion, they will still experience changes in their environments. For instance, the increased solar output could alter the atmospheres and climates of planets like Jupiter and Saturn, potentially impacting their moons, which might harbor conditions suitable for life. Increased radiation and solar wind effects might also reshape their magnetospheres. As the red giant phase progresses, the Sun will eventually shed its outer layers, creating a beautiful planetary nebula. This process will leave behind a dense core known as a white dwarf, which will continue to cool over billions of years. The expelled material from the Sun will enrich the interstellar medium with heavy elements, contributing to the formation of new stars and potentially new planetary systems. While this scenario seems distant and catastrophic, it is a natural part of a star's life cycle. It's crucial to understand that these processes occur over geological and astronomical timescales, providing ample time for humanity to explore options for cosmic survival, such as colonizing other celestial bodies or developing technologies to move away from the solar system if necessary. The transition of our Sun into a red giant will lead to extreme changes in the solar system, resulting in the destruction of the inner planets, including Earth, while providing the raw materials for new star formation in the galaxy. This cosmic event is a reminder of the dynamic and ever-evolving nature of the universe in which we live. Coronal mass ejections, or CMEs, are massive bursts of solar wind and magnetic fields rising above the solar corona or being released into space. These eruptions can unleash billions of tons of charged particles, primarily electrons and protons, into the solar system at speeds of up to several million miles per hour. When directed towards Earth, CMEs can pose significant threats to modern technology, particularly systems that rely on electronic communication and power distribution. One of the primary concerns associated with CMEs is their potential to disrupt the Earth's magnetosphere. As these charged particles interact with the Earth's magnetic field, they can induce geomagnetic storms. These storms can lead to fluctuations in the magnetic field that affect satellite operations, including communication satellites and navigation systems such as GPS. In extreme cases, CMEs can cause satellites to malfunction or degrade their functionality, leading to loss of data, disruption of services, and costly repairs or replacements. In addition to impacting satellites, CMEs can also pose a risk to power grids on the Earth's surface. The geomagnetic storms induced by CMEs can induce strong electric currents in power lines and transformers, leading to spikes in voltage. Such surges can damage transformer infrastructure, resulting in widespread power outages. Historical instances, such as the 1989 blackout in Quebec, demonstrate the potential for CMEs to cause significant disruptions in electricity supply when major geomagnetic storms occur. CMEs can also affect communication systems on Earth, disrupt radio signals, and increase the risk of interference in aviation communication. High-frequency radio communication, especially at polar latitudes, can be particularly vulnerable during geomagnetic storms, impacting aviation and maritime operations. Additionally, enhanced radiation levels due to CME activity pose risks for astronauts in space, necessitating the implementation of safety protocols during heightened solar activity. To mitigate these threats, scientists continuously monitor solar activity using satellites equipped with instruments designed to detect CMEs and other solar phenomena. Early warning systems can provide alerts when a CME is detected and forecast its trajectory toward Earth, allowing power grid operators, satellite managers, and other stakeholders to take precautionary measures. By preparing for the potential impacts of CMEs, we can enhance the resilience of modern technological systems against solar-related disruptions. Coronal mass ejections from the Sun pose significant risks to modern technology by disrupting satellite operations, power grids, and communication systems. Continued monitoring and preparedness efforts are essential to protect our technological infrastructure from the effects of these high-energy solar events. The potential consequences of a rogue planet entering our solar system are complex and could have significant implications for the existing dynamics of the solar system and the planets within it. Rogue planets are celestial bodies that do not orbit a star and travel through interstellar space. If such a planet were to enter our solar system, the outcomes would largely depend on its size, mass, trajectory, and proximity to other celestial bodies. One immediate concern would be gravitational interactions. A rogue planet passing close to the Sun or other planets could exert significant gravitational forces, potentially altering the orbits of planets, asteroids, and comets. These changes might lead to destabilized orbits for some of the outer planets, and this disturbance could send asteroids or comets into the inner solar system, increasing the risk of impacts with Earth or other planets. The gravitational pull could also threaten the stability of the Kuiper belt and Oort cloud, reservoirs of icy bodies that could become perturbed and enter new orbits. If a rogue planet were to approach Earth, the consequences could be more direct and severe. Depending on its size and trajectory, it could pose a threat of collision, which would have catastrophic effects, reminiscent of past impacts that have caused significant extinction events. Even if the rogue planet did not collide with Earth but passed within a close range, the gravitational influence could potentially affect Earth's rotation, tilt, and axial stability, leading to significant climate changes. In addition to gravitational interactions, a rogue planet may bring with it various materials, such as gases, dust, or icy bodies. These materials could be introduced into the solar system's environment and might even interact with existing planets or moons. Depending on their composition, such materials may lead to the emergence of new environmental conditions, potentially affecting the habitability of neighboring worlds. Moreover, the psychological and societal implications of such an event should not be overlooked. The discovery of a rogue planet entering our solar system could provoke public concern, scientific investigations, and discussions about planetary defense strategies. Efforts would likely intensify to monitor celestial movements and develop technologies to mitigate potential risks posed by rogue planets or other near-Earth objects. While the chances of a rogue planet entering our solar system are statistically low, the implications could be profound. The gravitational dynamics of our solar system and the potential for catastrophic impacts would warrant careful observation and preparation. Continued advancements in observational technologies and our understanding of celestial mechanics will be critical in enhancing our ability to detect and respond to such cosmic phenomena. The collision between the Milky Way and the Andromeda Galaxy, expected to occur in about 4 to 5 billion years, is a significant event in the future evolution of our universe. While the term collision may imply a cataclysmic crash, the reality is that such large-scale interactions between galaxies are typically complex and can result in dramatic changes over extended periods. One immediate implication of this galactic merger is the rearrangement of stellar orbits within both galaxies. As the two galaxies begin to interact gravitationally, many stars, including those in our solar system, will experience shifts in their trajectories. Although the distances between individual stars are vast, the gravitational forces at play can lead to alterations in orbits. Our solar system may be pulled into different regions of the newly formed galaxy, altering its position relative to other stars. Interestingly, despite the significant changes happening on a galactic scale, the chances of direct collisions between stars are exceedingly low due to the vast distances between them. However, the gravitational interaction could disturb the orbits of nearby stars and may affect the stability of objects throughout the solar system, including the Oort cloud, a distant region populated by comets and icy bodies. This disturbance could potentially send some of these objects into the inner solar system, increasing the likelihood of cometary activity impacting the planets, including Earth. The merger will also impact the structure and dynamics of the galaxies involved. As Andromeda and the Milky Way combine, they will potentially form a new galactic structure, often referred to as Milkomeda. During this process, many stars will be drawn towards the center as both galaxies feed into the newly formed core, which may eventually become an elliptical galaxy. In this evolution, the central regions of both galaxies could see bursts of star formation driven by gas and dust clouds being compressed during the merger. Additionally, the interaction may significantly expand the overall scale of the new galaxy formation. The gravitational forces at play can lead to the formation of new clusters and regions of stars and provide an opportunity for new solar systems to form over time. Overall, while the collision between the Milky Way and Andromeda galaxies will undoubtedly lead to substantial changes, our solar system is likely to endure this event largely intact. The timeframes involved are on a cosmic scale, and such interactions can take billions of years to fully unfold. Ultimately, the long-term effects of this merger will shape the future of our galaxy and potentially influence the conditions that could support life in the distant future. Cosmic radiation poses significant risks to the health of interplanetary travelers, and understanding its long-term effects is critical for planning missions to destinations such as Mars and beyond. Cosmic radiation consists primarily of high-energy charged particles from sources like supernovae and the Sun, which can penetrate spacecraft and human tissue, leading to several potential health concerns. One of the most serious long-term effects of cosmic radiation exposure is the increased risk of cancer. As high-energy particles interact with biological tissues, they can cause damage to DNA, leading to mutations that can result in cancerous growths over time. Studies suggest that astronauts on missions outside Earth's protective atmosphere risk cumulative doses of radiation that could significantly elevate their long-term cancer risk, necessitating careful monitoring and protection strategies. Another effect of cosmic radiation is acute radiation syndrome, though this is more likely in the event of a solar particle event rather than prolonged exposure. However, astronauts could also experience symptoms during long-duration missions due to the cumulative effects of lesser doses over time. These symptoms could include fatigue, nausea, or other short-term health issues that may complicate mission performance. Cognitive function and central nervous system health are additional areas of concern. Research indicates that exposure to high levels of radiation can have detrimental effects on the brain, potentially leading to cognitive decline, impaired memory, and psychological changes. For individuals on extended missions, maintaining mental health and cognitive performance is imperative, as these factors can impact mission success and crew dynamics. The reproductive health of interplanetary travelers could also be affected by cosmic radiation. Recent studies have suggested that increased radiation exposure may interfere with fertility, pose risks to embryonic development, or lead to genetic mutations that could affect future generations. This is a particular concern for long-duration missions where the exposure times are extended. To mitigate these risks, spacecraft designed for interplanetary travel will need robust shielding to protect occupants from cosmic radiation. This shielding can include materials such as polyethylene or water, which can absorb and deflect harmful particles. Furthermore, mission planning should incorporate monitoring systems to track radiation exposure and adjustments to crew schedules during solar events. Ultimately, addressing the long-term effects of cosmic radiation is essential for the health and safety of interplanetary travelers. Continued research into radiation protection, combined with advancements in spacecraft design and mission planning, is necessary to prepare for the challenges of deep space exploration, ensuring that astronauts can live and work safely in environments far removed from the protective cradle of Earth's atmosphere. Assessing and mitigating the risks of potentially hazardous near-Earth objects involves a combination of detection, tracking, characterization, and potential deflection strategies. NEOs, which include asteroids and comets, can pose significant threats to Earth if they collide with our planet. The increasing awareness of these risks has led to coordinated international efforts to better understand and prepare for potential impacts. The first step in risk assessment is detection. Numerous observatories and space missions around the world are dedicated to identifying NEOs through telescopic surveys. Programs such as NASA's Near-Earth Object Observing Program and the European Space Agency's Space Situational Awareness Program utilize ground-based and space-based telescopes to discover new objects, monitor their orbits, and provide early warning of potential threats. Automated systems help to analyze data and prioritize observations of newly found bodies to assess their orbits and potential risk levels. Once a NEO is detected, the next critical phase is tracking. Astronomers use precise measurements to calculate the object's trajectory and predict its future path. By determining the size, shape, and velocity of a NEO, scientists can evaluate whether it poses a collision risk within a given time frame. This tracking phase is vital for identifying any potential changes in an object's orbit due to gravitational influences, collisions with other objects, or effects from sunlight. The Palermo Technical and Torino scale are two commonly used systems for conveying the level of risk associated with NEOs. Characterization is also essential in understanding the composition and structure of NEOs. Knowing whether an object is solid rock, a loose rubble pile, or contains volatiles can inform potential mitigation strategies. Space missions, such as NEOWISE and the upcoming visits by the Double Asteroid Redirection Test mission, aim to gather detailed information about specific NEOs to allow for more accurate predictions and assessments. Mitigation strategies can be categorized into several approaches. One commonly discussed method is kinetic impactor technology. This entails sending a spacecraft to collide with a NEO to change its trajectory slightly. DART is designed to demonstrate this technique by impacting a binary asteroid system in the near future. Another approach involves gravitational tractor techniques, which involve positioning a spacecraft near an object to utilize its gravitational pull to slowly alter its path over time. In the case of larger NEOs that may be on a collision course with Earth, nuclear disruption methods have also been proposed, which could involve detonating a nuclear device near the NEO to deflect its trajectory. However, these methods require careful consideration and international cooperation to mitigate any unintended consequences. The involvement of national and international space agencies, scientists, and collaboration with private sector entities is crucial for effectively addressing the risks associated with NEOs. Ongoing research, awareness, and preparedness initiatives will enhance humanity's capability to detect, track, and potentially mitigate the threat posed by near-Earth objects, ensuring greater safety for our planet over the long term.